Hi everyone, welcome to goclasses. In this lecture, we will continue our complete summary of graph theory. So this is graph theory, complete summary part 4. The previous part you can find on the YouTube, on the goclasses YouTube channel. On the YouTube, you can search goclasses graph theory summary. You can see this playlist, you will find graph theory complete summary. Okay, so here you can find the part 1, part 2, part 3. Okay, and this is the gate 2006 question. So basically, these lectures you can find, and the link I will provide you in the description. Now let's study what are bipartite graphs. These are very special type of graphs. So let's see. Let me tell you that this type of graphs, these are called bipartite graph. The name itself is telling you the definition of bipartite. Bi means two. Okay, bi means two, and partite means partition, or I can say part. So you can see partite means part, or I can say partition. So what is a bipartite graph? Bipartite graph are those graphs in which we can partition the vertices into two parts such that every edge has one endpoint in this part, another endpoint in this part. Basically, every edge, if you see, that is going between the parts. Means in this part there is no edge, in this part there is no edge. Basically, all these vertices, they are non-adjacent, and these vertices, these are also non-adjacent. If you see, every edge is between these two parts, means every edge has one endpoint in this part and another endpoint in this part. So this type of graphs are called bipartite graphs. Let me tell you, if any undirected graph I give you, and if you can make the partition of vertices into two parts such that every edge will be between these two parts, okay, then this type of graph will be called bipartite graph. So you can see the definition. A bipartite graph, this is an undirected graph VE such that the set of vertices can be partitioned into two subset L comma R, where every edge has one endpoint in L, another endpoint in R. So very simple definition. If you have a graph GVE, when can I say this graph is bipartite? The name itself is telling you bipartite means two part, or I can say two-part partition. Okay, so basically this graph will be called bipartite if this vertex set, this I can say all these vertices, if I can divide them into two parts. Okay, of course these two parts must be disjoint. Okay, so the vertices that you have here and the vertices that you have here, they must be disjoint. Okay, so I can say that these two parts, they must not have anything common, their intersection must be phi. Okay, they must be disjoint. So I'm saying that if this graph, in this graph, if the set of vertices you can partition into two parts such that there is no edge between these vertices, there is no edge between these vertices. Basically, every edge has one endpoint here and another endpoint here. Okay, if every edge is like this, then in this situation we will say that this graph is bipartite graph. Okay, basically every edge is between these two parts. Okay, every edge has one endpoint in A, another endpoint in B. So this type of graph will be called bipartite graph. Remember, in this A, every two vertices, they must be non-adjacent. Means here in this part, if you take any two vertices, then these two they must not have any edge between them. Similarly, this in this part, if you take any two vertices, they must be non-adjacent. Okay, so I can say basically for any two vertices v1 v2 in the part A, what should happen? This v1 and v2, they should not have any edge between them. Okay, v1 v2, what should happen? They must be non-adjacent. Okay, they must be non-adjacent. Similarly, for B also the same thing you can say. In this B also, for any two vertices, I can say that they must be non-adjacent. And if there is any edge, then that edge must have one endpoint in A, another endpoint in B. So this type of situation must happen. So in this situation, we will say that this graph is bipartite graph. So read the definition. A bipartite graph is an undirected graph G, V, comma E, such that the set of vertices can be partitioned into two subset L, R, such that every edge has one endpoint in L, another endpoint in R. So this type of graph, these are called bipartite graph. For example, consider this graph. Is this bipartite graph? Let me tell you, yes, this is bipartite graph, because what I can do, I can partition these vertices. There are four vertices A, B, C, D. I can partition these vertices into two parts such that every edge will be between these two parts. Okay. So let me tell you what I will do. Notice this A I will put either in this part or in this part, yes or no, because every vertex I should put either here or here. So what I will do, let's assume that I am putting this A here. Now you can easily see I want to create a bipartition. I want to create a partition of vertices such that every edge will be between these two parts. So remember, in this part I cannot put B, okay, because if I put this B, this vertex B, if I put in this part, then what will happen? These are adjacent, there is edge between them. This is not what I want, okay. I want a bipartition, means every edge should be between these two parts, okay. So these are the two parts that I'm creating. So you can see if I put this vertex A here, then definitely this vertex B will be put here, and this vertex C, this vertex D also will be put here, okay, because you can see there is edge from A to B, okay, there is edge between A to B, and there is edge between AD. Now tell me where to put this vertex C. So you can see this vertex C I cannot put here, because if I put vertex C here, then these two are adjacent, C comma D, they are adjacent, okay. But you can see that I want to create a bipartition such that in this part every two vertices should be non-adjacent, in this part every two vertices should be non-adjacent, and every edge should be between these two parts. So what I will do, I will put this vertex C here. Now everything is fine, because you can see A comma C, they are non-adjacent, there is no edge between A comma C, and B comma D, they are non-adjacent, there is no edge between B comma D. So finally you can see this C is adjacent to D, this C is adjacent to B. So that's it. So for this graph we have this bipartition. That is the reason I can say this is a bipartite graph, okay. Is this clear? So remember this graph G, I can say this is a bipartite graph. And what is the reason? The reason is very simple, because for this graph I have a bipartition of vertices, two parts of vertices, such that every edge is between these two parts, okay. Now let's see this graph. Is this graph bipartite graph? Very simple, you can easily check. What you will do, see, if this is a bipartite graph, then you can create two parts of vertices, yes or no. You can partition the vertices into two parts, L comma R, such that every edge will be between these two parts. In this part every two vertices will be non-adjacent, in this part every two vertices will be non-adjacent. So what I will do, notice, let me put this vertex A here. Now if I'm putting this vertex A here, then definitely this vertex B comma D I should put in this part B comma D, okay, because there is edge between AB, there is edge between AD, okay. So if I'm putting this vertex A in this part, then definitely B comma D must be put in this part. Next you can see that where should I put this vertex C? Notice this vertex C I cannot put here, because these are adjacent, C comma D, they are adjacent. So I cannot put vertex C in this part. So definitely I will put vertex C in this part, because remember A comma C, they are non-adjacent. So everything is fine. Okay. Now where to put this vertex F? I cannot put vertex F here, because if I put here, then you can see there is edge between D comma F. Okay. So I cannot put vertex F here. So let me put vertex F here. Now there is nothing wrong. I can say basically everything is fine, because you can see all these vertices A, C, F, they are non-adjacent. Okay. So there is no edge between A, C, F. You can see. Okay. They are non-adjacent vertices. So finally I can say this F I will put here. And where to put this vertex E? This I cannot put here, because you can see B comma E, they are adjacent. So I cannot put vertex E in this part. So definitely what I need to do, this vertex E also I need to put in this part, okay. Now everything is fine. You can see in this part every two vertices are non-adjacent, in this part every two vertices are non-adjacent, and every edge is between these two parts. You can see what are the edges, okay. This AB, AD, and you can see this CD, CB, there is edge CD, CB. Also you can see there is edge EB, okay. And what else? You have FD, okay. There is another edge, the edge that is FD. So you can see that's it. So remember this graph, if you have this graph G, this is also bipartite graph. And the reason is very simple, because I can create a bipartition of this graph G such that every edge is between these two parts. What about this graph? Is this graph bipartite? This is your C5. I can say this is a simple cycle on 5 vertices. So tell me, is this graph bipartite? Now let me try to create a bipartition. Okay. Just let me try. What I will do, remember, I will try to create two parts of vertices such that these vertices are non-adjacent and these vertices are non-adjacent. Every edge will be between these two parts. Okay. Let me try. So let me put this vertex A here. Now you can see if I'm putting this vertex A here, then where I will put vertex B comma C, these vertices I need to put here. Okay. Next you can see where to put this vertex D. Definitely vertex D I cannot put here because you can see there is edge between B comma D. Okay, so I cannot put vertex D here. So let me put vertex D here. Now you can see everything is fine because these vertices are non-adjacent. These vertices are non-adjacent. Now where to put E? This is the question. If I put E here, then there is a problem because these are adjacent. Okay, so I cannot put E in this part, in this left part. Okay, let me put this E in this part. Now also there is a problem because these are adjacent. So you can see I cannot put this vertex E in this right part. So notice one thing. I cannot put vertex E in left part. Also, I cannot put vertex E in right part. So whatever you do, you can easily notice that this graph I cannot represent as a bipartite graph, or I can simply say that this graph is not bipartite graph. Is this clear? So remember, this graph is not. This is not bipartite graph. Okay, very simple. So easily you can prove that this graph is not bipartite graph with this logic, because where you will put E, that is the question. Okay, where this E will go. Okay, you cannot put E here. I cannot put E here, and of course I cannot put this E here. Okay, so that is the reason I can say that this graph is not bipartite. Let's see this question. Is this graph bipartite graph? Okay, again what we will do, we will try to create bipartition of this graph. So you can see A, B, C, D, and let's assume E, F, G, H. So let me try to create bipartition of this graph again. So here I will try to create I will try to create a partition of vertices into two parts L comma R, such that all the edges will be between these two parts. So let me put this vertex A here. If I'm putting this vertex A here, then definitely you can see that this vertex B, E, C, these vertices I need to put in the part R. Yes or no? Because you can see A is adjacent to B, B, E, and C. So, okay, these vertices I need to put in the part R. Now you can see everything is fine because B, E, C, they are non-adjacent. Okay. Next, you can see where to put the next vertex. For example, where to put this vertex G. You can see G I cannot put here because these are adjacent. So I will put this vertex G here. Okay. Next, you can see these are non-adjacent. So everything is fine right now. So far, everything is fine. Now, where to put this vertex F? I cannot put vertex F here because these will be adjacent. So let me put vertex F here. Okay, now you can see everything is fine because these are non-adjacent and these are also non-adjacent. Next, where to put this vertex H? So this vertex H, remember, this I cannot put here. If I put it here, then these will be adjacent. F comma H, they are adjacent, you can see. So I cannot put vertex H here. So let me put this vertex H here. Okay. Next, so where to put this vertex D? You can see this vertex D I cannot put here because H comma D, these are adjacent. So let me put this vertex D here. Now so far everything is fine. Now you can see all the vertices we have put. Yes or no? And you can see all these vertices, these are non-adjacent, and these vertices, these are also non-adjacent. And you can check every edge will be between these two parts. For example, you can see there is edge AB, AE, AC. Okay, so these are the edges you can see. So every edge is between these two parts. You can see in this part there is no edge, in this part there is no edge. So I can say this is perfect bipartition of these vertices such that all the edges will be between these two parts. So I can say this graph is bipartite graph. You can easily notice. Okay, I hope you understood. So very simple, this is the bipartition that will work. So this graph is also bipartite graph. This is also a BP graph, bipartite graph. I hope you understood all the things, all the concepts so far. So the definition of bipartite graph is clear. It is very simple. If you have a graph G, V, comma E, and remember, this graph will be called bipartite if there exist, remember, if you can create a partition of vertices into two parts such that all the vertices in this part will be non-adjacent, all the vertices in this part will be non-adjacent, every edge will be between these two parts. Okay, every edge will go between these two parts, means every edge will have one endpoint in this part, another endpoint in this part. If you can do this type of bipartition for graph G, then this graph will be called bipartite graph. Okay, so you can see this is the definition, a bipartite graph, or I can say bigraph. So this is a graph whose vertices can be divided into two disjoint subset such that every edge connects a vertex of set U to vertex of set V. Okay, so this is the simple idea. Now let me tell you the formal definition just for formality. Okay, let's see the definition of bipartite graph. So in the bipartite graph, some conditions that we need to satisfy. So let me explain. So if you have a graph GV, E. Okay, this is bipartite graph. Then you already know that we must have a partition of vertices into two parts. Okay, so basically this graph is, let's assume this graph is bipartite, then what should happen? Then this V I should be able to divide, remember this V I should be able to divide into two categories, or I can say two parts, A comma B. Now what are the properties of these two parts? The first property is that A union B must be equal to all the vertices, of course. Every vertex should be covered in A comma B. Okay, every vertex should be either here or here. Next you can see that they must be disjoint. A intersection B must be phi, means these vertices they must be disjoint. Basically this vertex set I'm dividing into two disjoint subsets. Okay, very simple. What are the third property? The third property is that all these vertices are non-adjacent. All these vertices are non-adjacent, or I can simply say that for every edge, what should happen? One endpoint should be in this part and another endpoint should be in this part. So I can say that for every edge, remember, this is the point. I can say that for every edge, one endpoint in A, another endpoint in B. One endpoint in A. Okay, every edge should have this. For every edge, one endpoint in A and one endpoint in B. This should happen for every edge. So this is the definition of bipartite graph. You can easily see here. So the definition of bipartite graph, a graph is bipartite. Okay, if this vertex set, the set of vertices can be partitioned into two set v1 comma v2 such that these properties must be satisfied. The union of v1 v2 should be v. The intersection of v1 v2 should be phi. They must be disjoint. And you can see if you take any vertex in v1, then it will be adjacent only to the vertices of v2. Similarly, if you take any vertex in v2, then they will be adjacent to only the vertices of v1. Okay, so very simple idea, and this is the definition. Now let's see a very important theorem related to bipartite graph. A graph is bipartite if and only if it doesn't have any odd length cycle. This is very important theorem for the bipartite graph, and in many questions you will apply this theorem. So please understand that a graph is bipartite if and only if, this is if and only if theorem, means if a graph is bipartite then it will not have any odd length cycle. Also, if your graph does not have any odd length cycle, then your graph will be bipartite. So this is a if and only if theorem. Okay, so a graph is bipartite if and only if the graph does not contain any odd length cycle. Okay, or you can say that a graph is bipartite if and only if every cycle in the graph must have even length. Okay, in the graph, every cycle, if there is a cycle, then it should have even length. Basically there should be no cycle which has odd length. Okay, there should be no cycle of length 3, length 5, length 7, length 9, and so on. Okay, so a graph is bipartite if and only if the graph does not have any cycle of odd length. This is very important theorem. Please understand, this is a if and only if theorem. So this is both ways. If your graph is bipartite, then there is no odd length cycle. Also, if the graph does not have any odd length cycle, then the graph is bipartite. Okay, so this is both the ways. Now let me tell you how to check if a given graph is bipartite or not. In the gate exam they will give you some graph and they will ask you, is this bipartite? So there are two methods to check whether a given graph is bipartite or not. The first method is you find odd length cycle in the graph. If there is odd length cycle, for example, if there is triangle, if there is 3 length cycle, 5 length cycle, 7 length cycle, and so on, if there is a odd length cycle, if you can see odd length cycle, then the graph is not bipartite. I told you that if the graph has odd length cycle, then it is not bipartite. If your graph is bipartite, then it will not have odd length cycle. Okay, and remember, if your graph is not bipartite, then it will definitely have odd length cycle. So very simple, how to check if a given graph is bipartite or not? So the method number one is find odd length cycle. If there is odd length cycle, then the graph will be not bipartite. You can see a graph is bipartite if and only if there is no odd length cycle. Okay, so this is if and only if theorem. If there is no odd length cycle, then the graph will be bipartite. And if there is odd length cycle in the graph, then the graph will not be bipartite. The method number two, this is another method which is very useful. Remember, okay, method number one, method number two, both are very useful. So let's see the method number two to check if a given graph is bipartite or not. Very simple. Try to create a bipartition of vertices such that all the edges are between the two parts. Very simple. Okay, if a graph is given to you, let's assume a very big graph is given to you, maybe 10 vertices. Okay, maybe 20 vertices or whatever. So you can see what you can do. You can try to create a bipartition of the vertices. Basically, the vertices you divide into two parts such that all the edges will be between the two parts. Okay, so this is the idea. Try to create a bipartition of vertices so that all the edges are between the two parts. If you can create this type of bipartition, okay, then the graph will be bipartite. Or if there is any, I can say, if there is any contradiction, then in this situation I can say the graph will not be bipartite. Okay, so these are the two methods. So let's see some questions, a lot of questions we are going to see. Let's solve this TIFR question. Which of the following graphs are bipartite? So three graphs are given to us. Let's check, are they bipartite or not? So you tell me about the first graph. Is this graph bipartite or not? Very easily you can see this graph has a odd length cycle. Okay, just look at these vertices, this vertex. Okay, just look at these vertices and tell me this cycle. Look at this cycle. Is this odd length cycle or not? This cycle. Yes, this is a odd length cycle. Yes or no? Very simple. Okay, so you can easily see this graph has five length cycle. Yes or no? From here, this vertex, look at this vertex A, B, C, D, E. Okay, so there is a five length cycle. Very easily. This is a very easy question, you can easily see. Okay, in this graph, immediately you can see there is a five length cycle. Okay, look at this outside. So you can easily see that there is five length cycle. So because this graph contains odd length cycle, so this graph is not bipartite. A graph is bipartite if and only if there is no odd length cycle. This graph contains some odd length cycle. There is at least one odd length cycle in this graph. So this graph is not bipartite. Okay. So very simple that this graph is definitely not bipartite. What about this graph, the graph number 3? What about this? Here you can easily see there is a triangle. Okay, this is also nothing complicated. You can easily see there is a triangle in this graph. Just look at this graph. So there is a triangle. So remember in this graph also there is a odd length cycle. So this graph is also not bipartite, because remember, if the graph has some odd length cycle, any odd length cycle, then the graph is not bipartite. What about this graph, graph number 2? This graph number 2, if you observe, this does not have any odd length cycle. Okay, in this every cycle has even length, so this will be bipartite. Now how to prove it? How to prove that this graph is bipartite? So let me tell you, what you can do, you can try to create a bipartition. See, this graph is given to you. For this graph and this graph, you can easily see that they are not bipartite because there is odd length cycle. Okay, in this graph very easily you can see that there is odd length cycle. Okay, so you can easily see this is the odd length cycle. Next, in this graph also this is the odd length cycle. So these two graphs very easily you can see that these are not bipartite. But what about this graph? Okay, if you look at this graph, you will see that there is no odd length cycle because it is looking like every cycle has even length. Yes or no? Okay, look at this. So every cycle seems to have even length. But how to be sure? If you want to be sure that this graph is bipartite, then what you do? You create a bipartition. Very simple. Okay, so let me call these vertices, for example, A, B, C, D, E, F, G, H. Okay, now let's try to create a bipartition. So I will try to partition the vertices into two set L comma R. Okay, so that all these vertices will be non-adjacent. All these vertices will be non-adjacent. Basically, every edge will be between the two parts. Okay, so if I can create this type of bipartition, then I can say that this graph will be bipartite. Okay, so let me start with vertex A. Let me put vertex A here. If I put vertex A here, then you tell me where to put vertex B, C, G, because you can see this A is adjacent to B, C, G. So you can see if I put vertex A here, then B, C, G must go here. Now tell me, are these three vertices, are they adjacent? So you can see vertex B, vertex C, vertex G, they are non-adjacent. Yes or no? Whatever two vertices you take here, they are non-adjacent. So everything is fine. So far everything is fine. Now let's see where to put the remaining vertices. For example, where to put the vertex D? Okay, you can see this vertex D I cannot put here because these are adjacent B comma D. So they are adjacent. So I cannot put vertex D in this part. So let me put vertex D here. You can see they are non-adjacent. A comma D. They are not adjacent. So everything is fine. Okay. Now where to put the next vertex? For example, F. This vertex F I cannot put here because these will be adjacent D comma F. So I cannot put vertex F in this part L. So let me put vertex F here. Now you can see everything is fine because you can see this BF, these are non-adjacent, CF non-adjacent, GF non-adjacent, yes or no? So you can see these vertices, they are pairwise non-adjacent. So everything is fine. So far, everything is correct. Okay. What about the next vertex? So you can see A, B, C, D, we have covered. Next, this vertex E. Tell me, what about the vertex E? This vertex E I cannot put here because you can see CE, they are adjacent. So vertex E I cannot put here. Let me put vertex E here. Is everything fine? Yes, everything is fine because you can see AE, they are non-adjacent. What about DE? They are non-adjacent. So everything is fine. Okay, and where to put the last vertex, that is H. So this vertex H, where to put it? You can see this vertex H I cannot put here because GH, they are adjacent. So I cannot put vertex H here. If I put vertex H here, HF, they are adjacent. Okay, so let me put vertex H here. Now you tell me, this H, is this adjacent to these vertices? You can see AH, DH, EH, they are non-adjacent. So that's it. So this is the correct bipartisan. Every edge will be between the two parts. Okay, every edge will have one endpoint in L, another endpoint in R. So that's it. So finally I can say this graph, okay, this graph, this second number graph, this is a bipartite. So this is the TIFR question. I hope you understood. So finally, for this question, which graph are bipartite? The answer will be only two. This is a very simple question. I hope you understood. Let's solve this question. Which of the following graph are bipartite? This graph, is this bipartite? Yes, of course, there is no odd length cycle. I told you a graph is bipartite if and only if there is no odd length cycle. In this graph, there is no odd length cycle. There is no cycle at all. Yes or no? So you can see, yes, this graph is bipartite. Okay. Or if you want, you can create the bipartisan also. See this graph, in this graph, there is no odd length cycle. There is no cycle at all because there is no odd length cycle. So this is bipartite. Okay. Very easily you can see this is bipartite. Now, if you want, you can create the bipartisan also. So let me create the bipartisan. The bipartisan you can create like this. What you can do, you can put vertex C here and you can put vertex ABDE here. Now you can easily see every edge is between these parts. Okay. Is this clear? So you can see these vertices, these are non-adjacent. So finally I can say, yes, this is the correct bipartisan. So this graph, this is bipartite graph. But easily you can see there is no odd length cycle. So definitely this is bipartite. Okay. What about this graph? Let me know. What about this graph? Before that, let's see this graph. In this graph, do you see any odd length cycle? Yes, I see. Okay, I can see that this triangle I can easily see. Okay. Okay, can you see? Look at this graph. Just look at this graph. Can you see this triangle? There is a triangle here. So because there is a triangle means there is a odd length cycle. Yes or no? There is a three length cycle. This graph contains odd length cycle. There is at least one odd length cycle in this graph. So this graph is not bipartite. Okay, very easily you can see. What about this graph? This graph, it is looking like bipartite because it looks like that, okay, every cycle has even length. Okay, if you see, for example, if you see this cycle, this also has even length. But what you can do, if you want to be sure this is bipartite or not, then what you can do, you can create a bipartisan. Okay, so let me create a bipartisan here. This is vertex A, B, C, D, E. Okay, so what I can do, very simple, let me try to create a bipartisan. Let me put vertex A here. If I put vertex A in this part L, then I have to put vertex B, vertex E, and vertex D in this part R. Yes or no? Now you can see everything is fine because B, E, and D, you can see they are non-adjacent. So everything is fine. Now where to put this vertex C? I can put this vertex C here because AC, they are non-adjacent. Now that's it. This is the perfect, I can say, bipartisan. So that's the reason I can say this graph is also bipartite. I hope you understood. Tell me the answer for this question. Are these graph bipartite? Let's look at this graph. In this graph, easily you can see there is a triangle. There is a odd length cycle. Look at this B, E, D. So you can easily see this triangle you can easily find. So because this graph H has a triangle, this graph has at least one odd length cycle. So this graph is not bipartite. The theorem is very simple. If your graph is bipartite, then there should be no odd length cycle. And if there is at least one odd length cycle, then the graph is not bipartite. So the theorem is actually if and only if your graph is bipartite, if and only if there is no odd length cycle. Okay, so you can see in this graph there is a triangle. In this graph H, okay, you can easily see, look at this BED. So that is the reason I can say this graph, this is a not bipartite. What about this graph G? So this graph G looks like complicated graph. So the best way, what is that? That is create a bipartisan, because this is looking like a complicated graph. Okay, so what you can do, you can try to create a bipartisan L comma R. So we will try to partition the vertices into two parts such that every edge should be between these two parts. Okay, so let's start. Let me put vertex A here. Then automatically, because this vertex A is adjacent to G, F, E, C. So you can see G, F, E, C. I have to put in this part. Now you make sure. Okay, what you check? You check are they adjacent. So you can check that GF, these are not adjacent. Next G, F, E and C. So you can see they are non-adjacent. Okay, whatever two vertices you take here, you can check they are non-adjacent. So everything is fine. Okay. Now where to put the remaining vertices? So for example, where to put the vertex B? You can see if I put vertex B here, there is a problem because these are adjacent. C comma B, they are adjacent. So let me put vertex B here because A comma B, they are non-adjacent. Okay, so now everything is fine. Now where to put the remaining vertices? For example, this vertex D, where to put the vertex D? So this vertex D, if I put here, if I put the vertex D here, then there is a problem because ED, these are adjacent. So I cannot put vertex D here. Okay. So where to put D? Let me put D here. Now you can easily see that AD, they are non-adjacent, and BD, these are also non-adjacent. So yes, this bipartisan, this is perfect. Yes or no? This is correct. You can see all the edges are between these two parts. Every edge has one endpoint in L, another endpoint in R. So I can say this is a bipartisan of this graph G, I can say. So that is the reason this graph G, this is a bipartite graph. Okay, is this point clear? So very simple, this graph G, this is bipartite. Now let's move on. Now let's see this theorem, and this is very easy to prove. If G is a bipartite graph and the bipartisan is X and Y, basically the set of vertices we divide into two parts that are X comma Y, then the total degree of part X is equal to the total degree of part Y. Can you prove it? This is very intuitive. You can easily prove it. Okay, see what I'm saying that G is a bipartite graph, and there are these are the bipartisan. Bipartisan is X comma Y. So you can see the bipartisan is X, Y. This is the bipartisan. Now what we need to prove? We need to prove that if you do the total degree of part X, means in this part, for if you do the degree summation of all the vertices, also in this part, if you do the degree summation of all the vertices, then that will be equal, the total degree of this part will be equal to the total degree of this part. This is what we need to prove. You can easily see here we are doing the total degree, the degree summation we are doing. Summation of degree of vertices in the part X is equal to summation of degrees of vertices in the part Y. So the total degree of part X equal to total degree of part Y. This is what we need to prove, and this is very easy to prove. What is the reason? Because remember, this is a bipartite graph, so every edge will connect one vertex from here to one vertex from here. Yes or no? Every edge, what it will do, if I put some edge, let's assume if I put this edge, then what will happen? The total degree of part X will increase by 1, and the total degree of part Y also will increase by 1. Okay, is this clear? So if I put this edge, because of this edge, the total degree of part 1, this total degree of part X increasing by 1, and total degree of part Y increasing by 1. Okay, you can put another edge. For example, let me put this edge also. Now also you can easily see the total degree of part Y increasing by 1, total degree of part X increasing by 1. You can put another edge. For example, let me put this edge. Then again the same thing. Total degree of part Y increasing by 1, total degree of part X increasing by 1. So what I'm saying, you can see that every edge, because of every edge, whatever edge you put, because this is a bipartite graph, so every edge will have one endpoint in X, another endpoint in Y. So because of every edge, the total degree of this part will increase by 1, and the total degree of this part will increase by 1. So finally I can say the total degree of this part and total degree of this part will always be equal. Yes or no? Is this clear? So I can say that summation of degree of vertices in part X, that will always be equal to this value will always be equal to summation of degree of vertices in part Y, of vertices in part Y. Okay, is this clear? Very simple. So this is very easy to prove. Let's solve this question. A graph is called k regular if every vertex has degree k. This is the definition we already know. This is the definition of k regular graph. A graph is regular if every vertex has same degree, And a graph is k regular means every vertex has degree k. Prove that if a bipartite graph is also k regular, then both the part they will have same cardinality. Number of vertices in both the part will be same. So this is actually very easy to prove. Here you can see that you have a bipartite graph. For this bipartite graph we need to prove. Okay, so if you have a bipartite graph, here you have two parts. This is part A, this is part B. Now we are saying that this bipartite graph is k regular means here every vertex has degree k, here also every vertex has degree k, and we already know that in the bipartite graph the total degree of part A will always be equal to total degree of part B. Yes or no? So you can easily see, if I do the total degree, the degree summation of vertices of part A, that will be equal to the degree summation of vertices of part B. This we already know in the bipartite graph, this will always happen. Okay, now you tell me what is the total degree of part A. In this part A you can see every vertex has degree k. Okay, every vertex that is having degree k, so the total degree will be number of vertices in part A multiplied by k. Okay, because every vertex had degree k, we are saying that this bipartite graph is k regular. Okay, so that is the reason I can say the total degree of this part, that will be number of vertices in this part multiplied by k is equal to the total degree of this part will be number of vertices in this part multiplied by k. Okay, now from here k you cancel, finally number of vertices in part A equal to number of vertices in part B. Very easy to prove. These are simple things. If you just understood the definition of bipartite graph, then you can easily solve all these questions. Let's study the next topic, that is complete bipartite graph. Let's see what is this. Complete bipartite graph, the name itself is telling you, first of all, this is a bipartite graph. Okay, so remember, this is a bipartite graph means the vertices I can partition into two parts, part A comma B, such that every edge will be between these two parts. Okay, so complete bipartite graph, this is a bipartite graph, but there is one more property. The name is telling you complete. Okay, what it means, it means that every vertex in this part A will be adjacent to every vertex in this part B. This is the definition of complete bipartite graph. Okay, so remember, complete bipartite graph is a bipartite graph, so there will be partition of vertices into two parts A comma B. Okay, such that every edge will be between these two parts. So this is what bipartite graph says. But what this complete bipartite graph says, complete means that every vertex in this part will be adjacent to every vertex in this part. Okay, so it will happen like this. If you take for all x in part A, for all y in part B, what will happen? This xy will be edge. This xy is an edge. This xy, this will belong to the edges. So this is the idea. This is the definition of complete bipartite graph. Okay, means let's assume that you have two vertices here, and let's assume you have three vertices here. Then remember what will happen, that every vertex will be adjacent to every vertex. Every vertex of part A will be adjacent to every vertex of part B. This type of graph are called complete bipartite graph. Now here you can see that cardinality of vertex, this set A, that is 2, and here you can see that cardinality of this set B, that is 3. So this complete bipartite graph, this is written as km comma n, or I can say you can write it, what is m? M is the size of A. M is the size of A, and n is the size of B. Okay, and remember, n is the size of B. So complete bipartite graph we represent by Kmn. Kmn means m vertices here, n vertices here, and remember every vertex of this part will be adjacent to every vertex of this part. So this type of graphs are called complete bipartite graph. So you can see this is K23. K23 is the complete bipartite graph. One part has two vertices, another part has three vertices. You can see every vertex in this part is adjacent to every vertex in this part. Similarly, this is K33. Here you can see this part has three vertices, this part has three vertices, K33. Now again, every vertex of this part is adjacent to every vertex of this part. Similarly, K35. Here you can see there are three vertices here and there are five vertices here. So this is K35. Complete bipartite graph simply means that every vertex of this part will be adjacent to every vertex of this part. Similarly, this is K26. One part has two vertices, another part has six vertices, and you can see every vertex in this part is adjacent to every vertex in this part. So this is the definition of complete bipartite graph. Now let's see the properties of complete bipartite graph KMN. So tell me, what will be the number of vertices in KMN? Number of vertices in this complete bipartite graph KMN. Very simple. The number of vertices will be m plus n, because remember, in this KMN, this is the notation for complete bipartite graph, and here this m is the size of one part and this n is the size of another part. Okay, it will happen like this, that one part will have size m. Okay, so let's assume this is your part A and this is your part B. We are doing the partition of vertices into two parts, such that here remember that size of A is m and here size of B is n. Okay, so this is the complete bipartite graph. The total number of vertices, what that will be? That will be m plus n. Can anyone tell me the what is the number of edges? What will be the number of edges? That will be mn, because every vertex here will be adjacent to every vertex here. Yes or no? So remember, this vertex will be adjacent to every vertex here, this vertex will be adjacent to every vertex here. So you can see total number of edges, what that will be? That will be mn. Next, tell me, what will be the maximum degree in this graph? In this complete bipartite graph, what will be the maximum degree? You can easily see one thing, that what will be the degree of this vertex? Tell me, in this part A, the degree of this vertex, what that will be? You can see this vertex will be adjacent to every vertex in part B. So what will be the degree of this vertex? The degree of this vertex, let me call it degree of this vertex, for example, 1. Okay, or I can say, maybe let's call it P. So tell me, what the degree of this vertex P? That will be n. Yes or no? Because this vertex is adjacent to every vertex in part B. Similarly, take any vertex of part B, that will be adjacent to every vertex of part A. Yes or no? So tell me, what the degree of this vertex? So the degree of this vertex, that will be n. Yes or no? Okay, here you can easily see, for this vertex, the degree that will be m. Okay, because this vertex will be adjacent to every vertex in set A. So tell me, what will be the maximum degree? The maximum degree will be the maximum value of m comma n, because remember, these vertices have degree n, these vertices have degree m. Okay, is this clear? So the maximum degree will be whatever is the maximum value of m comma n. If m is maximum, if this set is bigger, then the degree will be m. If n is maximum, if this set is bigger, then the maximum degree will be n. What will be the minimum degree? That will be minimum of m comma n. Okay, so these things, these small things, you can easily see. And what will be the degree sequence? That also you can easily find. The degree sequence, tell me, what will be the degree sequence? You can see all the vertices in set A, these have degree n. Yes or no? So remember, n and so on. How many times? How many times we will have this degree n? That will be m times. Yes or no? Okay, so this will be m times. And how many times we will have degree m? We will have degree m. That will be n times. Okay, this will be n times. So this is the analysis of complete bipartite graph. I hope you understood. So remember, whenever you see this notation KMN, this is complete bipartite graph. Is this clear? This is not the notation of bipartite graph. This is the notation of complete bipartite graph. It means that there is partition of vertices into two parts, such that this part has number of vertices m and this part has n vertices. And remember, every vertex here will be adjacent to every vertex here, and every vertex here will be adjacent to every vertex here. Basically, every vertex in one part is adjacent to every vertex in another part. So please understand, this is the notation for complete bipartite graph. This is not the notation for bipartite graph. This is the notation for complete bipartite graph. Now let's see one concept, that is star graph. Let me tell you K1n, this is called star graph. What is K1n? This is the complete bipartite graph where one part has one vertex, another part has n vertices. So star graph, the definition of star graph is K1n. This is called star graph. And what is the reason? See, I told you that K1n, this is the complete bipartite graph. You can see K1n. And this graph is called star graph. And let me tell you the reason. The reason is very simple. For example, consider K1, K13. Okay, if you see K13 means one part has one vertex and another part has three vertices, and you can see this is complete bipartite graph. So this type of graph, why this is called star graph? This is called star graph because you can draw it like a star. You can draw it like a star. Okay, is this clear? So you can see this K1n, this is called star graph because we can draw it like a star. For example, let's look at K14. This K14 you can draw like this. Okay, so you can draw it like a star. So that is the reason this is called star graph. Very simple definition. Remember, K1n. This is complete bipartite graph where one set has one vertex, another set has n vertices. So this K1n, this is called star graph. For example, K13, K14. Okay, so these are star graph. Tell me the answer for this question. In a bipartite graph, ABE. So what this notation means, first of all, this notation simply means that the vertices we have partitioned into two set. So these are the parts of the vertices, basically part A, part B. Okay, is this clear? Every edge is between these two parts, means every edge has one endpoint in part A, another endpoint in part B. So this is the notation. So in a bipartite graph G, A, B, E, so these are the vertices and these are the edges. So these are the two parts of the vertices AB, where the part A has three vertices, part B has five vertices. What are the maximum number of edges that we can have? Maximum number of edges that will be, if you want to get maximum number of edges in a bipartite graph, then what you can do, you can create a complete bipartite graph and the answer will be 3 into 5, that will be 15. Okay, very simple. If I want maximum number of edges in a bipartite graph, then what you will do, in a bipartite graph, if I want maximum number of edges, then I will create a complete bipartite graph. Okay, is this clear? So the maximum number of edges will be 15. Now let's see maximum number of edges in a bipartite graph on n vertices, how to find. If your bipartite graph has total n vertices, then what will be the maximum number of edges in the bipartite graph? Let's solve this question. In a bipartite graph, if there are 6 vertices total, then what are the maximum number of edges? Can you think about it? Total we have 6 vertices and the graph is bipartite. Okay, number of vertices, that is 6, and your graph is bipartite. Now you tell me what is the maximum number of edges that we can have. Now you might be thinking that it will depend on which part has how many vertices, yes or no. You might be thinking that. For example, let me give you some scenario. If I put one vertex here, if I put one vertex here, and if I put 5 vertices here, then tell me how many edges, maximum how many edges I can have. If I have this type of situation, then maximum how many edges I can have. Then here maximum number of edges I can get is 5. Okay, but what I can do, instead of doing this, what I can do, I can put 2 vertices here and I can put 4 vertices here. Okay, yes or no? So now you tell me, in this situation, what will be the maximum number of edges that I will get? Okay, I can put 2 vertices in one part and 4 vertices in another part. Now in this situation, what will be the maximum number of edges that I will get? That will be 2 into 4. Okay, that will be 2 into 4, that will be 8. Okay, so you can see definitely this is better than this situation, because remember in the question this is given to us that you have total 6 vertices. We don't know which part has how many vertices. Please understand, total 6 vertices we have. Okay, which part will have how many vertices, we don't know. This part has how many vertices, this part has how many vertices, we don't know. Okay, so either we can create this situation here, maximum we can get 5 edges. In this situation we can get maximum 8 edges. Now there is another possibility. What I do, I put 3 vertices here and I put 3 vertices here. In this situation, maximum how many edges I will get? I will get, that is 3 into 3, that will be 9. Yes or no? So if I put 3 vertices in one part, 3 vertices in another part, then in this situation I will get maximum number of edges I will get, that will be 9. Now you can easily see definitely this value is maximum. Okay, here I'm getting 5 edges, here I'm getting maximum 8 edges. So definitely this 9, this is the maximum number of edges I can get. I hope you understood. Okay, is this clear? So very simple. Maximum number of edges that we can get, the answer for this question, that will be 9. And when it will happen, tell me? It will happen when we put 3 vertices in one part and remaining 3 vertices in another part. In this situation, we will get maximum number of edges, and that will be 9. I hope you understood. So tell me, if you have n vertices, then what will be the answer? Maximum number of edges in a bipartite graph on n vertices. Again, you already know that we don't know in which part we are having how many vertices, we don't know. Yes or no? Ultimately, in the bipartite graph, we have total n vertices, and we want to find how many maximum number of edges I can put. Okay, so let's see how to solve it. See, very simple. I know that this is a bipartite graph, so definitely there will be two parts of the vertex set. Yes or no? So this is the partition of the vertices into two parts. Let me call it part A, let me call it part B. Now I don't know which situation will give me maximum number of edges. Do you agree with me? Okay, how many vertices I should put here, how many vertices I should put here, I don't know which situation will give me maximum number of edges, I don't know. Okay, so let me put m vertices here. Let me put m vertices here. Okay, I don't know how many vertices I should put here so that I can get maximum number of edges. So let me put m vertices here. Okay, m is the variable. Now tell me how many vertices will be there here. That will be automatically n minus m. Okay, so tell me maximum in this situation, maximum number of edges that I will get, what that will be? In this situation, maximum number of edges that I will get, that will be m multiplied by n minus m. Okay, here you tell me which is variable and which is constant. In this situation, you can see that this m is the variable because n is the constant. Yes or no? Is this clear? So remember here, this variable, this is the variable, this m is the variable. Do you agree? M is the variable because remember this is fixed, this is constant. Yes or no? This n value, this is not a variable, this is constant. Okay, for example, on 10 vertices, on 20 vertices. Okay, so this n is the constant, but m is the variable. Okay, so this I can say that this is function of which variable? This is function of variable m. Okay, because n is already constant, so this is variable, this is function of variable m. Now what we want to do, we want to maximize this. Do you agree? This is what we want to maximize it. Yes, do you agree with me? This value I want to maximize because remember, this is the number of edges. This m multiplied by n minus m. This is the number of edges. I want to get maximum number of edges. I don't know for which value of m I will get maximum number of edges. I don't know. How many vertices I should put here? How many vertices I should put here? I don't know which will give me maximum number of edges. So I'm putting m vertices here, and this is variable. So you can see this is the number of edges that I will get. So I want to maximize this value. Now you already know maxima minima, that concept you already know. So let's just apply that concept. So tell me, this is fm, that is m multiplied by n minus m. Okay, let's try to maximize this value. This value we need to maximize. Okay, so for which value of m this function will maximize? Okay, so let's see what you will do. You will find the derivative, yes or no? So you will find df dm. Okay, now tell me what that will be. You can easily see this is basically mn minus m square. Okay, so mn, that will be basically n, minus this will be 2m. Okay, now what we do to maximize this? What we do, we put it equal to 0. Okay, from here what we got n equal to 2m. Basically m is equal to n by 2. Are you getting my point? Let me know. Okay, so that's it. So this value means m equal to n by 2. This value will maximize the number of edges in the bipartite graph on n vertices. So that's it. Finally, we got this answer. Okay, so let me tell you the answer. So maximum number of edges in the bipartite graph on n vertices, what that will be? That will happen. Remember, that will happen when you put n by 2 vertices here and n by 2 vertices here, half vertices here, half vertices here. Then in this situation you will get the maximum number of edges, and that will be n by 2 whole square. Okay, is this clear? The answer, this will be the answer. I hope you understood. Okay, so you can see maximum number of edges in the bipartite graph on n vertices. Maximum number of edges in the bipartite graph, what that will be? That will be n by 2 multiplied by n by 2, n by 2 whole square. Okay, now you might be thinking, sir, if n is odd value, for example, if number of vertices, if that is for example 7, then what to do? If n is odd, okay, for example if n is 7, then what to do? Then very simple, then you have to put half vertices here, but you cannot put 3.5 vertices here, yes or no? So very simple, what you can do, you can put 3 vertices here and you can put 4 vertices here. Is this point clear? Please tell me. So if n is equal to odd, then in this situation what you need to do, very simple point, then here in this part you need to put, I can say for example n by 2 seal. Here if you are putting n by 2 floor, then in this part you have to put n by 2 seal. Okay, so your answer will be, if n is odd, then remember the maximum number of edges, that will be, in one part you put n by 2 floor, in one part you put n by 2 seal. This is the answer. I hope you understood. Okay, so remember, you can put this if n is even, and you can put this equation, n by 2 floor multiplied by n by 2 seal, if n is odd. Okay, understood? Please tell me. Very simple. Let's solve this GATE 2014 question. The maximum number of edges in a bipartite graph on 12 vertices. So we have a bipartite graph, total number of vertices is 12, and we want to find maximum how many edges we can have. So this is very simple. I told you, if you have a bipartite graph on n vertices, then the maximum number of edges, if you have this value, this is your value of n. So if you have a bipartite graph on n vertices, then remember the maximum number of edges, that is basically n by 2 floor multiplied by n by 2 seal. Okay, here you can easily see n is 12, so n by 2 floor, n by 2 seal, that will be 6. So finally the maximum number of edges, that will be 6 multiplied by 6, that is 36. Now let's see a note. N vertices bipartite graph, maximum how many edges it can have? It can have n by 2 whole square edges. Yes or no? If you have a bipartite graph with n vertices, then maximum, remember maximum I can put n by 2 whole square, these many edges I can put. Do you agree with me? Okay, this we have already seen, that if you have a bipartite graph on n vertices, then this is the maximum number of edges I can put. Okay. So, if a graph on n vertices has more than these edges, then it cannot be bipartite. Okay, this is very interesting result. Please focus here. We have already seen that n vertices bipartite graph can have maximum these many edges. Okay, n by 2 whole square, maximum these many edges we can have in a bipartite graph on n vertices. So, if graph has n vertices and more than these edges, means more than n by 2 whole square edges, if your graph has more than these many edges, then definitely it is not bipartite. Do you agree? Yes or no? So this is the point, that if a graph on n vertices has more than n by 2 whole square edges, then it is not bipartite. You can see, can you prove it? This theorem we have already proven, that prove that n vertex graph with more than n square by 4 edges is not bipartite. This is what we have already proven. Please tell me, did you understand? Because remember, if you have n vertex bipartite graph, then the maximum number of edges you can have, that is n square by 4. Now, if you have more than these many edges, more than n square by 4 edges, then definitely your graph is not bipartite. We have already proven it. Let's see one more result, that is hypercube graphs. These are bipartite. We already know what is a hypercube graph. Hypercube graph, that is represented by Qn. And what is this Qn? In this Qn, the vertices are set of all n length binary strings. And what are the edges? The edges are between two vertices. We put edge if they differ in exactly one bit position. So in this hypercube graph Qn, the vertices, remember these are n length binary strings. For example, in Q3, the vertices will be 3 length binary strings. So there will be total 2 power 3, means 8 vertices. And 2 vertices are adjacent if and only if they differ in exactly 1 bit position. Okay, so this is the hypercube graph that we already know. Now let me tell you that these hypercube graphs, these are bipartite. Okay, so can we prove it? Let me tell you, very easily you can prove. And for that, let's see the definition of parity. What is parity of a bit string? Parity of a bit string, that is very simple, that is either odd or even, and that is determined by number of ones in the string. See, very simple concept. If I give you a bit string, for example 0 1 1 0 1, now if I ask you what the parity of this, then remember the answer will be odd or even. Parity of a bit string, that is odd or even, answer will be odd or even, and that will be determined by number of ones. Here in this string, how many ones you have? Total 3 ones you have. So number of ones is odd, so the parity of this string is odd. I hope you understood. For example, if I ask you what the parity of this string, the parity of any bit string, that will be odd or even, and that is determined by number of ones. For example, in this string, how many ones you have? There is no one, or I can say there is 0 1, so there is even number of ones, so the parity of this string will be even. Okay, understood. For example, if I ask you what are the parity of this string, the parity of this string will be even. Okay, so this is the concept parity of a bit string. Very simple thing, that parity of a bit string is odd or even. Any bit string you take, for example, if I ask you what is parity of this string, then that also will be even. Okay, so you can see parity of a bit string is odd or even, and it is determined by number of ones in the string. Now let me prove that hypercube graphs are bipartite. And how to prove it? It is very simple. If you want to prove some graph is bipartite, then what the easy way is, you create a bipartition such that all these vertices are non-adjacent, every edge is between these parts, yes or no. So if you can create this type of bipartition, then you can prove that the graph is bipartite. Okay, for hypercube graph, what I can do, notice one thing, very simple. For hypercube graph, the bipartition will be like this, that in one part I will put odd parity strings, in this part I will put even parity string. Very simple point. Okay, in one part, in this part I will put odd parity strings, and in this part I will put, basically in one part I will put odd parity strings, and in another part I will put even parity strings. Okay, is this clear? If you do this, then definitely you will see that these vertices are non-adjacent. There is no edge between these vertices, there is no edge between these vertices. Okay, every edge will be between these parts. Okay, every edge will have one endpoint here, another endpoint here. Okay, and you can easily see this. Tell me one thing, if two vertices are here, can they be adjacent? A very simple question I'm asking. Okay, take example of q3. Take example of q3. In q3 the vertices are three length binary strings, yes or no? Okay, so in q3 you can easily see that what I will do, I will create two parts such that here I will put even parity strings, and here I will put odd parity strings. Okay, what are the even parity three length strings? Because q3 has vertices which are three length binary strings, so even parity strings, for example, this is even parity string, this is even parity string, and so you can see these are even parity strings. Okay, these four are even parity string. Next, what are odd parity string? You can see, for example, this is odd parity string. Next, you can see this is also odd parity string, this is also odd parity string, and this is also odd parity string. Okay, now you tell me, now you tell me, here you notice, these are they adjacent? Tell me quickly, are they adjacent? This and this, they are not adjacent, because you can see they differ in two positions. Are they adjacent? No, they differ in two positions. Are they adjacent? No, they differ in two positions. Are they adjacent? No, they differ in two positions. Okay, are they adjacent? No, they differ in two positions. So you can easily see that these are non-adjacent, and these are also non-adjacent. Okay, so very easily you can see that these are non-adjacent, these are also non-adjacent. So I can say this is a bipartition, yes or no? Okay, is this clear? Every edge will be between these two parts. For example, this will be adjacent to this one and this one. Okay, is this clear? For example, you can easily see that this will be adjacent to this one, this one, and this one. Okay, I hope you understood the point. Okay, so Easily you can easily see that this is the bipartition of Q3. So please tell me, did you understand that hypercube graph are bipartite? Because what I can do, I can create a bipartition of the vertices such that in one part I will put even parity strings, in another part I will put odd parity strings. Now you can easily see that these strings, these are non-adjacent, and these strings, these are non-adjacent. And what the reason? See, the reason is very simple, because take any string. Okay, for example, let's take Q5. In this Q5, if you take any string 0, 1, 1 like this, now you can see this is an odd parity string. Okay, this is an odd parity string. Tell me, this will be adjacent to whom? Let me know. This string will be adjacent to whom? See, this will be adjacent to those strings which differ by this string in only one bit position. Yes or no? So you can easily see, if you change, for example, this bit, if you change this position, then what will be the parity of this string? This will have parity, even parity. Yes or no? This has even parity. Similarly, you can notice that if you change, for example, this position, then what you will get? Then also you got even parity. Okay, I hope you are understanding the point, that very simple, that this string, if you see what which string this will be adjacent to, then this odd parity string, this will be adjacent to even parity string only. Okay, odd parity string cannot be adjacent to odd parity string. Okay, odd parity string, they can never be adjacent. Similarly, even parity string, they can never be adjacent in Qn. Yes or no? In the hypercube graph. That is the reason what you can do for this hypercube graph, you can create the bipartition. Okay, in one part you put even parity string, another part you put odd parity string. You can easily see these are non-adjacent. Okay, and these are also non-adjacent. So this is the bipartition. So I can say this hypercube graph, this is bipartite graph. I hope you understood. So we have seen hypercube graph are bipartite. Let's see the next topic, that is cyclic graph and acyclic graph. The name itself is telling you cyclic graph means graph containing at least one cycle. Acyclic graph means graph containing no cycle. The name itself is telling you cyclic means graph containing at least one cycle. Acyclic means graph containing no cycle. So a graph with no cycle is acyclic. And let me tell you, another name for acyclic is forest. Okay, acyclic graph, the another name is forest. Okay. So for example, here you can see in this graph there is a cycle. This is the cycle. So this graph is a cyclic graph because there is a cycle here. And in this graph there is no cycle. We do not have any cycle here. So this is acyclic graph. So you can see graph with no cycle is acyclic. Graph with at least one cycle is cyclic. Okay. Also, you understand the difference between cyclic and cycle graph. If you remember, we have already seen that cycle graph is something like this. It is a simple cycle. Okay, for example, what is C5? C5 will be a simple cycle. This type of cycle. Basically, cycle graph. Remember, cycle. Cycle graph is simple cycle. And what is cyclic graph? Cyclic graph is graph containing at least one cycle. For example, look at this graph. This graph is not cycle. Yes or no? Is this cycle graph? Is this cycle graph on 5 vertices? No. Is this cycle graph on 4 vertices? No. So remember, this graph is not cycle graph. This is not cycle graph, but this is cyclic graph. Okay, is this clear? This graph is a cyclic graph. So this difference, you understand that cycle graph simply means it is a simple cycle. A graph which is simple cycle graph, that means a graph which is simple cycle. For example, here you can see this is C6. This is a graph on 6, this is a cycle graph on 6 vertices. This is cycle graph on 5 vertices. Basically, Cn means a simple cycle on n vertices. Okay, so you can see. And what is cyclic graph? That is a graph containing at least one cycle. So this graph contains a cycle. So this is cyclic graph. So remember, these are different. Cyclic graph and cycle graph, they are different. Now let's see acyclic graph or forest. I told you that another name for acyclic graph, that is forest. Okay, these are same. These things, these are same. Please understand that forest, acyclic graph, these are same. Acyclic graph is also called forest. And acyclic graph is not necessarily connected. It may be connected, remember. For example, this is connected. This is also acyclic graph, or I can say this is also forest. This is also forest, remember. because you can see there is no cycle here. So this is acyclic graph, or I can say forest. And this is also forest. This is also acyclic graph, because this is also, this does not have a cycle. So you can see this is also acyclic graph, or I can say this is also a forest. I hope you understood. So remember, acyclic graph may or may not be connected. Okay, acyclic graph or forest is not necessarily connected. It may be connected, it may be disconnected, but the point is acyclic means a graph containing no cycle. So what is a cyclic graph? That you already know, graph containing at least one cycle. Okay. Now tell me one thing. In a cyclic graph, there is at least one cycle. Now can I say that there are at least two vertices which have more than one path between them? Just think about it. In a cyclic graph, there is a cycle that you already know. Okay. In a cyclic graph, there exists a cycle. Okay. This type of cycle will be there. Of course, there can be some extra things, remember. Of course, there can be some extra things. I don't know. Okay, some extra vertices can be there. I don't know. Okay, there can be some extra vertices. Remember, some extra things can be there. I don't know. But the point is, there is a cycle. There exists a cycle. Cyclic graph means there exists a cycle. Now, there are at least two vertices which have more than one path between them. Yes, this statement is true, because consider this vertex A and consider this vertex B. Now these vertices have more than one path between them. Okay, you can see, look at this path. This is path 1. This is a, I can say this is path 1. And look at this path. Look at this path. This is path 2. I hope you understood. So remember, this is the definition of cyclic graph, that there are at least two vertices which have more than one path between them. This is the definition of cyclic graph. So cyclic graph has two definitions now. There are two definitions for cyclic graph. Graph containing at least one cycle. The definition number 2, that is, there are at least two vertices which have more than one path between them. So these are the two definitions of cyclic graph. Similarly, there are two definitions of acyclic graph. Definition 1, that is, graph containing no cycle. Definition 2 is, every pair of vertices, between any two vertices, there is at most one path. Why at most one path? Because acyclic graph can be disconnected. Yes or no? It may be disconnected, it may be connected, or it may be disconnected. So that is the reason I can say acyclic graph means between every two vertices, whatever two vertices you take, there will be at most one path between them. Now let's study a very important topic, that is trees. Trees in graph theory, and this is most important topic in graph theory. Many questions come from trees. So we will do the complete analysis of trees, and we will see a lot of questions based on trees. So let's see what are trees in the graph theory. The definition is very simple. A tree is connected acyclic graph. So you can see a connected acyclic undirected graph, that is a tree. So remember, tree means connected also and acyclic also. These two conditions must satisfy. Okay. So this is very important, remember, because a lot of questions based on tree, where you have to understand that these two properties must satisfy to become a tree. A graph is a tree, undirected graph. Trees are undirected graph, remember. Okay, undirected graph is tree if it is connected and acyclic. These two properties must happen. It must be a connected graph and it must be acyclic. Okay, for example, you can see forest. Forest means acyclic. This can be disconnected also. For example, this is a forest. This is not tree because this is not connected. Okay, this is not connected, so this is not a tree. This is forest because there is no cycle, so this is acyclic. Forest means acyclic. This is also forest. Okay, you can see this is also forest. Every tree is a forest because there is no cycle, so this is forest. Yes or no? Forest means acyclic. There is no cycle here, so this is also forest. But remember, this is tree also because this is connected forest. Tree means connected forest, or I can say tree means connected acyclic graph. There is no cycle here and this is connected, so this is tree. Similarly, this is tree, okay, because this is connected and there is no cycle. Okay, I hope you understood. So let's see these diagrams. In these diagrams, you can see this is a forest, but this is not a tree. Yes or no? Because this is disconnected. This is acyclic, so this is forest. What about this? This is not even forest. There is a cycle here. Okay, there is a cycle here. So this is not even forest, this diagram. This graph is not a forest, this graph is not a acyclic graph, this is actually cyclic graph. So this is not a tree, not a forest. This is a tree because this is connected acyclic. This is also a tree because this is connected acyclic. Okay, let's see these diagram. This graph, this is connected acyclic, so yes, this is a tree. And this is a forest but not a tree. This is not connected, so this is not a tree. But this is acyclic, so this is forest. Acyclic means forest. Okay, both are same. So you can see what is the definition of tree. Tree is undirected graph which is acyclic, which is connected. These three properties must satisfy. Okay, remember in the graph theory, tree is undirected graph which is cyclic and connected. It must be connected and it must be cyclic. There should be no cycle and it must be connected. These graphs you can see, this is a tree, you can see this is connected and there is no cycle. This is not a tree, there is a cycle here. This is not a forest also. Okay, because there is a cycle here, so this is not a forest. What about this? This is a tree because this is connected acyclic. What about this? This is not connected, so this is not a tree. But this is a forest. Okay, yes or no? This is acyclic graph. This is forest, but not tree. This is not a forest, not a tree. This is a tree and also a forest. This is a tree, also a forest. Let's see these diagrams. In these diagrams, which is a tree, which is a forest? Tell me. Here you can easily see this is connected and acyclic. So this is forest, also tree. Yes or no? I can say this G1. I can say this is tree. Every tree is forest, remember. What about G2? Can you tell me about G2? G2, that is also tree because this is also connected acyclic. What about G3? What about G3? In G3, there is a cycle. You can easily see that there is a cycle. Look at this. A, then D, then E, then B. Okay, look at this. A, B, E, D, A. So there is a cycle. So you can see this is actually cyclic. So this is not a tree, not forest. What about G4? G4 is not connected, but this is acyclic. So this is a forest. Okay, remember this is not a tree. G4 is not a tree. What is the reason? Because this is not connected. You can see this AF, this is not connected. There is no path between A comma D, between A comma B. Okay, so you can see G, this is not tree, but this is a forest. This is acyclic graph. Okay, you can see this is cyclic graph, so this is not a forest, not a tree. Okay, this G3, if you look at this G3, this is not a tree. Okay, not a tree. So very easily you can see. This is a meme. You can see a tree with a cycle. Of course, remember, tree does not have a cycle. Okay, tree is acyclic connected graph. So we have seen that every tree is a forest. Okay, forest means acyclic graph. Every tree is a forest, but forest may or may not be a tree. Okay, because remember, forest may be disconnected. Okay, so forest may or may not be a tree, but every tree is a forest. Okay, we have seen the definition of forest. Forest are acyclic graph without a cycle. And what is a tree? Tree is connected forest, or I can say connected acyclic graph. You can see this is one graph. Okay, remember this is a single graph. This is one graph. So tell me, is this tree or forest? Let me know. Yes, this is a forest, but this is not a tree. Okay, because this is not connected. So this is a forest, but this is not a tree. Now let's do the complete analysis of tree. A tree is connected acyclic undirected graph. I told you that in the graph theory, tree is undirected graph and tree is connected acyclic. So these two properties are very important. The tree has these two properties. It must be connected and it must be acyclic. Okay. Tell me how many edges will be there in the tree on n vertices? A tree on n vertices will have how many edges? So let's try to find out. Let's assume that you have three vertices. Okay, let me assume you have three vertices and I'm creating the tree. So on one side I am writing number of vertices, another side I am writing the number of edges. Okay, number of vertices, that is n, and another side I am writing number of edges. So you tell me, if you have three vertices and I want to create a tree, tree is connected acyclic graph. So let me know how many edges I will put. Okay, right now is this tree? No, this is not connected, so this is not a tree. I want to create a tree, so let me create a tree. Okay, I can put this as, but this is not connected. Tree is connected acyclic, so let me put this as also. Now tell me, can I put this as? Let me know. Can I put this as? I cannot put, because now there is a cycle. Tree is connected acyclic. Okay, so you can see if you have three vertices, then there will be only two edges. Okay, you can easily see if I put this as, then there is a problem. Now this is not a tree. If I don't put this as, then this is not connected, so this is not a tree. So you can easily see if you have three vertices, then definitely number of edges will be two. Yes or no? Now what about the four vertices? For example, if I have four vertices, let me put vertex D here. Now you tell me how many edges I can put. Right now, is this tree? No, this is not a tree because this is not connected. Okay, I have to make it connected. Yes or no? Let me make it connected. So now this is connected. Now you can see there are four vertices, three edges. But you tell me a simple point. Can I put this edge? I cannot put it because now there is a cycle. Can I put this? Now there is a cycle. Can I put this? Now there is a cycle. So I hope you understood that this is connected as cyclic graph. So if you have four vertices, there will be three edges. Okay, what about the next vertex? You tell me about the next vertex. For example, right now this is not connected, so this is not tree. Okay, now I have to make it connected. If I want a tree, then I have to make it connected. Let me do this. Okay, let me put this as. Now this is connected. Now you tell me, can I put this as? No, because this will be cyclic. Okay, now this is not a tree. If I put this as, now this is not a tree, there is a cycle. So I hope you understood that if you have five vertices, then there will be four edges. So like this, you can easily see if the tree has n vertices, then number of edges will be n minus 1. Okay, so this is very simple point that every tree, remember, every tree on n vertices has number of edges equal to n minus 1. So if you have a tree on n vertices, then number of edges will be n minus 1. And remember, tree is connected and acyclic. These two properties must satisfy. Now let me tell you, there are many definitions of trees. In the GATE exam, they can give you different definitions, and they can ask you, is this definition of tree? Is this not a definition of tree? So actually there are many definitions of tree. So far we have seen one definition, that is tree is connected acyclic graph. Yes or no? Tree is connected and acyclic. So this is one definition. Let me tell you, whenever a graph is connected and acyclic, if these two properties are satisfied, then definitely it will be tree. Okay, and every tree is connected acyclic. So this is the definition, remember. This is the definition. What it means, if it is tree, then these two properties will satisfy, and if these two properties satisfy, then it will be tree. So this is one definition of tree, but there are many definitions of tree. Now can you find which is the definition of tree? For example, in the GATE exam, if this type of question comes, they are asking you which of the following defines tree on n vertices. So there are three things, there are three statements given to you, and you have to find which of the following will define a tree on n vertices. Then how to find it? How to check which is the correct definition of a tree? So let me tell you, to find what defines a tree, whenever you want to find that which statement is the definition of tree, then you do this. Always remember that these two properties means that it is a tree. Okay, connected and acyclic, these two properties must be there if you want to say that something is tree. Tree is connected and acyclic. Okay, also the second method, that is take four or five vertices and try to violate tree. Okay, what to do? See, for example, I will give you some statement will be given to you, and I will ask you, is this definition of tree? This statement, does it define tree? Then what you can do, you can simply take four or five vertices. For example, four or five vertices you can take, and then what you can do, you can try to create a situation where this will satisfy, but it is not a tree. Okay, is this clear? Some statement is given to you, then what you try to do, you try to make sure that this statement is satisfied, but still this is not a tree. So this type of graph you try to create. Okay, if you can create a graph which is not a tree, but this statement is satisfied, then I can say this statement is not the definition of tree. I hope you understood. Okay, is this point clear? Basically, you create a counter example. Yes, if any statement is given to you and they ask you, is this statement a definition of tree? Then you try to create a counter example. Take three or four vertices or four or five vertices. Then you try to create a graph where this condition, this statement is satisfied, but this graph is not a tree, then you can say this statement is not the definition of a tree. Okay, and tell me one thing, if you want to create a graph which is not a tree, then what you can do? If you want to create a graph which is not a tree, then what you can do? Either you create a disconnected graph, yes or no? If you create a disconnected graph, then definitely it is not tree. Or you create cyclic graph, means either you create disconnected graph or you bring a cycle. Then in this situation, your graph will not be a tree. Okay, so this is what I'm saying, that if you want to find what is the definition of a tree, then you can take 4 or 5 vertices and you can try to create a counterexample. You can try to violate tree. If you cannot violate, then it is the definition of tree. Okay, and you remember that tree means connected and acyclic, so these two properties must be there to be a tree. Tell me the answer for this question. Which of the following defines trees on n vertices? Means which of them is the definition of tree on n vertices? Let's see one by one. Tell me, is this the definition of tree? Undirected graph with n minus 1 edges on n vertices. Can I say this is the definition of tree? If you have undirected graph on n vertices, n minus 1 edges, then can I say this is the definition of tree? The answer is no. This is not the definition of tree. For example, take take 4 vertices and n minus 1 edges. Okay, so number of edges, that is a 3. Now can you create a graph which will satisfy this condition but it is not a tree? Can you create this type of graph? Basically I am taking 4 vertices, remember, I have taken 4 vertices and 3 edges. I need to put 3 edges. Okay, so what I can do, I can put 3 edges like this. Yes or no? Now you can easily see that condition is satisfied but this is not a tree. Okay, so this is the counter example. I hope you understood. This is the counter example. So you can see that this is not the definition of tree. Is this clear? So please understand, very important point, you try to understand that. Very important point, that if you have a tree, then there will be n minus 1 edges. Okay, is this clear? Every tree has n minus 1 edges. But if you have n minus 1 edges, then it does not mean it is a tree. Okay, is this clear? Very simple. Now tell me the answer for this question. Connected graph with n minus 1 edges. Now, is it the definition of tree? Connected graph, you must create a connected graph with n minus 1 edges. Then can I say, is it the definition of tree? Now the answer is yes. Okay, you can easily check. Okay, see, take number of vertices equal to 5. I told you take 5 vertices and you try to violate this condition. So let me try to violate this condition. Sorry, let me try to create a graph such that this condition will satisfy but it is not a tree. Okay, this is what I will do. Basically this statement is given to you. What I will do, I will satisfy this statement and I will try to create a graph which is not a tree. But if I cannot do, then I can say this is the definition of tree. Okay, so let me take 5 vertices. Then the question is saying connected graph with n minus 1 edges. So number of edges is 4 and this must be connected. This must be connected. Okay, so let me create a graph. Let me take 5 vertices A, B, C, D, E. Okay, so tell me right now, is this a counter example? Is this a counter example? No, because remember I need to create a connected graph. I must create a connected graph, yes or no? Okay, so you can easily see connected graph I need to create with 4 edges. I have to put only 4 edges. I only have 4 edges. For example, I can put this edge. Okay, now, is this connected? No, this is not connected. I have to put another edge. Is this connected? No, this is not connected. Okay. Can I put this edge? Yes, I can put this edge, but now I only have one edge. See, I can put this edge, yes, but now I only have one edge. So can I make it connected with only one edge? Can I make it connected? No, I cannot make it connected. So remember, this edge I cannot put. Okay, is this clear? So if I want to make it connected, then definitely what I need to do, you can easily see I will get a tree. This is what I'm saying. I'm saying that this statement, as if you try to create a counter example, then you cannot create a counter example. So is it the definition of tree? The answer is yes. Is this point clear? Connected graph with n minus 1 edges, that is the definition of tree. Please tell me, did you understand this point? I am saying that this statement as is given to you, connected graph with n minus 1 edges. So if you satisfy this statement, and then you try to create an example which is not a tree, it is not possible. You cannot create a counter example, you cannot create a graph which is not a tree but this condition is satisfied. So this type of counter example you cannot create, so I can say this is the definition of tree. I hope you understood. So remember, connected graph with n minus 1 edges, that is the definition of tree. That is another definition of tree. Tell me the answer for this question. Acyclic graph with n minus 1 edges. Is this the definition of tree? Acyclic graph with n minus 1 edges. So this is the statement S. Is this the definition of tree? The answer is yes. Again, the same thing you do. You take 5 vertices, okay, and n minus 1 edges means number of edges equal to 4, and the graph must be acyclic. The graph must be acyclic. So you tell me, if I take, let's assume 5 vertices, okay, is this counter example? No, this is not the counter example because I need to put 4 edges. Yes or no? I must put 4 edges and it must be acyclic. I cannot bring a cycle. So I need to put 4 edges. For example, if I put one edge here, one edge here, can I put this edge? I cannot put because I need a acyclic graph. So I cannot put this edge, remember. Okay. So you can see I need to put 4 edges. These are 2 edges. 2 more edges I need to put. Now you can easily see I will get a tree. Okay. So remember, this is the definition of tree. This is another definition of tree. Acyclic graph with n minus 1 edges. So tell me the answer. Which of the following defines a tree on n vertices? The answer will be graph with n minus 1 edges. The answer is no. Connected graph with n minus 1 edges? Yes. Acyclic graph with n minus 1 edges? Yes. Okay, is this clear? Connected graph with n minus 1 edges, that is the definition of tree. Acyclic graph with n minus 1 edges, that is also the definition of tree. Tell me the answer for this. Connected graph with minimum number of edges, is this the definition of tree? Connected graph with minimum number of edges. Connected with minimum number of edges, is this the definition of tree? The answer is yes. Again, the answer is yes. You can easily check. Okay. So this is connected graph with minimum number of edges. You can see, if I give you, let's assume 5 vertices, and you create a connected graph with minimum number of edges, means minimally connected. Please understand. You create a minimally connected graph. So you can easily see, if you create a minimally connected graph, means connected graph with minimum number of edges, then will you put this edge? Tell me. If you create connected graph with minimum number of edges, you have to use minimum number of edges, then will you put this edge? You will not put this edge, yes or no? You will make the graph acyclic. Okay, just think about it. If you create a connected graph with minimum number of edges, then definitely you will create a acyclic graph. I hope you understood. Because see, you will never create a cycle. If I tell you that please create a connected graph with minimum number of edges, then will you ever create a cycle? Will you ever create a cycle? Tell me. Will you create this type of thing? You will not create, because you can simply remove this edge is not required to make connected graph. Yes or no? This edge is not required to make the graph connected, so you can remove this. So if I tell you that create a connected graph with minimum number of edges, then you will create a acyclic graph. You will not create a cycle. You will create a acyclic graph. And remember acyclic connected graph, that is tree. Okay, so you can easily see that minimally connected graph is tree. Connected graph with minimum number of edges, that is tree. Tell me the answer for this question. Acyclic graph with maximum number of edges. Acyclic graph. You create a acyclic graph with maximum number of edges. Means your graph must remain acyclic. Please understand. Your graph must remain acyclic, but you must put maximum number of edges. For example, right now this is acyclic. Please see this. Look at this. This is acyclic. But did I put maximum number of edges? See, this is acyclic, but I can put this edge also. Now also this is acyclic. Can I put more edges and keep it acyclic? Can I put more edges and keep this graph acyclic? Yes, I can do this. Now also this graph is acyclic. So this graph, does it have maximum number of edges? Maximum number of edges? No. I can put this edge and still this is acyclic. Can I put one more edge? Tell me, can I put one more edge? I cannot put. If you put this edge, then there is a cycle. If you put this edge, there is a cycle. If you put this edge, there is a cycle. Whatever you do, if you put this edge, there is a cycle. Whatever you do, if you put one more edge, there will be cycle. So remember, acyclic graph with maximum number of edges means maximally acyclic. This is the definition of tree. And tell me the answer for this question. Is this the definition of tree? There is exactly one path between any two vertices. Look at this, exactly one path. I am saying between any two vertices, there is exactly one path. So between any two vertices, if you have exactly one path, exactly one means not more than one, not less than one. Yes or no? If you have exactly one path, then definitely it is connected. Okay, every two vertices, they have path between them, so this is connected. Whatever two vertices you take, between these two vertices there is exactly one path, not more than one, not less than one. So definitely this graph is connected. Yes or no? Okay, yes, this graph is connected. And also, because you have exactly one path between any two vertices, okay, only one path between any two vertices, then definitely this is acyclic. So you can easily see that acyclic connected. Yes, this is the definition of tree. I hope you understood. So we have seen many different definitions of trees. Finally, this is the conclusion. These are the definitions of trees. In the GATE exam, they can ask you which is the definition of tree. So you can easily see these are the definitions of trees. I told you that connected with n minus 1 edges, that is the definition of tree. We have already seen this, connected with n minus 1 edges. Similarly, acyclic with n minus 1 edges, that is also the definition of tree. Minimally connected is the definition of tree. Maximally acyclic is the definition of tree. Any two vertices are connected by unique path. There is exactly one path between any two vertices. That is also definition of tree. So you can see these on your screen. These are the definitions of trees. For example, you can easily see minimally connected. This is the definition of tree. Maximally acyclic. This is the definition of tree. Acyclic and connected. This is the definition of tree. Connected with n minus 1 edges. Connected with n minus 1 edges, that is the definition of tree. Acyclic with n minus 1 edges, that is the definition of tree. Uniquely connected means there is exactly one path between two vertices, that is also the definition of tree. So on your screen, all these are the definition of trees. Let me tell you, forest means acyclic graph, I told you, but forest can be disconnected also. Tree means cyclic connected. Tree is always connected. Tree is connected forest, I can say. Every tree is forest, but every forest is not tree. Forest can be disconnected, but tree is always connected. Let's see another thing. In the forest, I can say that between any two vertices, there is at most one path. Do you agree with me? Because the forest can be disconnected. Okay, for example, this is also forest. Look at this. There are five vertices. This is also the forest. You can see. Here you can see between these two vertices, there is no path. But between this vertex and this vertex, there is only one path. So you can see forest is acyclic graph. So between any two vertices, there will be at most one path. And in the tree, what happens? Tree is connected acyclic graph. So between any two vertices, there will be exactly one path. Whatever two vertices you take, there will be one path, and there will be only one path. Between any two vertices, there will be exactly one path, not more than one, not less than one. Let's see the next point. On n vertices, connected graph with minimum number of edges, that is tree. This we have already seen. That if you create a connected graph with the minimum number of edges, you try to connect a graph with the minimum number of edges, then definitely you will get a tree. So you can see on n vertices, connected graph with minimum number of edges is tree. Minimally connected. Yes or no? Every minimally connected graph is tree. So you can see connected also n minus 1 edges. This is the definition of tree. Okay, is this clear? Similarly, similarly, acyclic graph with maximum number of edges, that is also a tree. Yes or no? So you can see acyclic graph with maximum number of edges. Acyclic graph with n minus 1 edges, that is the definition of tree. All these definitions we have already seen. What is a tree? Tree is connected graph with minimum number of edges. I can say minimally connected. I can also say tree is acyclic graph with maximum number of edges. Means tree is minimally connected. Also, tree is maximally acyclic. These two statements, please understand. Tree is minimally connected graph. Any graph which is minimally connected with minimum number of edges, that will be tree. That is the definition of tree. Also, Any acyclic graph with maximum number of edges, that is the definition of tree. Okay, look at this point. In a tree, if I add one more edges, then what will happen? Tell me. Just look at this. For example, let's assume I have a tree. Okay, this tree I have. I'm giving you some tree. Tell me, in this tree, if I add one more edge, then what will happen? In this tree, add any more. For example, if I put this edge, then there will be cycle. Yes or no? There will be cycle. There will be cycle. If I add one more edge, then there will be cycle. And there will be how many cycles? Tell me. For example, any two vertices you take in this graph, any two vertices. For example, let me take this vertex and this vertex. If I put one edge, then how many cycles will come? Only one cycle will come. Yes or no? Tree plus one edge, that means cyclic graph with one cycle. Okay, is this clear? So remember, let me write it here, that a tree plus one edge. Tree plus one edge. Please understand, tree plus one edge, that is a cyclic graph with one cycle. Okay, is this clear? Cyclic graph with one cycle. And what about tree minus one edge? Tell me, from the tree, if I remove one edge, let's assume you have this tree, and if I remove some edge, this tree you have. Now tell me, if you remove some edge, for example, if you remove this, then it will be disconnected. If you remove this, disconnected. If you remove this, disconnected. If you remove this, disconnected. So this is what I am saying, that tree minus one edge, that is disconnected forest. Yes or no? So did you understand this? Tree plus one edge, that is cyclic graph with exactly one cycle, not more than one, not less than one. Okay, so tree plus one edge, that is cyclic graph with one cycle, and tree minus one edge, that is disconnected forest. Tell me the answer for this question. Which of them is the definition of tree? Which of the following is a tree? So you can see acyclic graph, no. Acyclic graph means forest, but tree is connected forest. Connected graph, no. Tree is connected acyclic graph. Connected acyclic graph, the answer is yes. Okay, option C, that is correct. What about the next? Connected with minimum number of edges. Yes, that is correct. Minimally connected. Minimally connected. Yes, that is correct. Okay. Tell me the answer for this question. What is a tree? N vertices, n minus 1 edges. No, this is not a tree. Okay. Yes or no? N vertices, n minus 1 edges. This is not the definition of tree. Connected with n minus 1 edges. Yes, that is the definition of tree. Maximally acyclic. Yes. Every two vertices have unique path. Yes. So B, C, D. These are the definition of trees. Let's solve this TIFR 2011 question. Which of the following is not a sufficient and necessary condition for undirected graph to be tree? See, the question is asking sufficient and necessary condition. Sufficient and necessary, it automatically means definition. The question is asking for definition of tree. This is asking for definition of tree. See, sufficient and necessary means if and only if statement. Sufficient and necessary, it means this is if and only if statement. So basically the question is asking that which of the following is not a definition of tree. I hope you understood. Which of the following is not a definition of tree? So you can see this is the definition of tree, that tree is acyclic connected. So yes, this is the definition of tree. This is a tree. What about this? Acyclic and connected. Yes, this is also the definition of tree. I told you that every acyclic and connected graph, that is a tree. So you can see acyclic connected n minus 1 edges. Yes, this is the definition of tree. Connected and n minus 1 edges. Yes, this is also the definition of tree. So this is also the tree. Acyclic and n minus 1 edges. Yes, this is also the tree. So what the answer? The answer is option E. N minus 1 edges. This is not the definition of tree. Okay. For example, I can create a counter example. Okay. Let's see. For option E, I can create a counter example. Consider this graph where I have 4 vertices and number of edges I will give you 3. Okay. Because option E, that is saying that G has n minus 1 edges. Okay. N minus 1 edges. So you can see I am giving you, this is n minus 1. So n minus 1 edges. But what I can do? This does not mean that it will be a tree. I can create this type of graph. In this graph, you have n minus 1 edges, but this is not a tree. Okay, yes or no? But this is not a tree. So you can see option E, that is not necessary and sufficient condition for tree. Tell me, let me know one thing. What about this option E? Is this necessary or sufficient or what? Tell me. Let me know. So here I am asking, see, these are necessary and sufficient for tree. All these are the definitions of trees. All of them. These are the definitions. These means these are the necessary and sufficient for tree. These are necessary and these are sufficient for tree. Okay. Now you tell me, what about option E? Is this necessary for tree or is this sufficient for tree? This is necessary for tree. Yes or no? This is necessary but not sufficient. See, this is not enough to make a tree. Please understand. If you have n minus 1 edges, that is not sufficient to make a tree. But if you have a tree, then it is necessary that you have n minus 1 edges. So please understand this option E, that G has n minus 1 edges. This is necessary condition for tree. This is necessary but not sufficient. Okay, very simple. Now let's do many questions related to trees and forest, because in the gate exam, in the TIFR, in exams, a lot of questions are coming from trees and forest. So we are going to do a lot of questions related to tree comma forest now. Tell me the answer for this question. What is the maximum number of edges in a forest on n vertices? If you have a forest acyclic graph on n vertices, then what the maximum number of edges you can put? That will be n minus 1, because you know that acyclic graph with maximum number of edges, that is tree. Yes or no? We already know forest with maximum number of edges, that is a tree. And in a tree, how many edges you have? That is n minus 1. Yes or no? So maximum number of edges that you can put in a forest, that will be n minus 1. Tell me the answer for this question. What is the maximum number of edges I can put in a forest which is not a tree? What is the maximum number of edges in a forest which is not a tree? Now the answer will be n minus 2. Okay, because remember, in a forest, if I put n minus 1 edges, then it will become a tree. Okay, we already know that forest with n minus 1 edges will become a tree. Okay, so please understand, in a forest, you have a forest. In this forest, if I put n minus 1 edges, if I put these many edges, then definitely this whole thing will become a tree. Okay, so how many edges I can put in a forest which is not a tree? The answer will be n minus 2. Okay, so for this question, which is not a tree, forest but not a tree, then maximum number of edges, that will be n minus 2. Tell me the answer for this question. What the minimum number of edges you can put on a connected graph? We know that minimally connected graph is tree. So you can see that connected graph with minimum number of edges, that is a tree. So tree means minimally connected. Okay, so you can see minimum number of edges in a connected graph, that will be n minus 1. Okay, is this clear? In a connected graph, the minimum number of edges will be n minus 1, because minimally connected graph is a tree, and in a tree we have n minus 1 edges. Tell me the answer for this question. What the minimum number of edges in a connected cyclic graph? What is the minimum? I want minimum number of edges such that the graph must be connected. See, the graph is connected and the graph has a cycle. Okay, and the graph must have a cycle. So you can easily see the answer will be what? Answer will be n edges. Okay, because if you put connected plus n minus 1 edges, then it will be a tree, and tree has no cycle. Yes or no? Are you getting my point? So this is what I'm saying, that if you put connected, if you make connected graph and plus n minus 1 edges, if you put n minus 1 edges, now this is the definition of tree, and tree has no cycle. This is the definition of tree, but tree is acyclic. So if you want cycle, then one more edge you have to put. So the answer will be n edges. Okay, very simple point. Tell me the answer for this question. What is the minimum number of edges in a connected acyclic graph? What are the minimum number of edges in a connected acyclic graph? Remember, connected acyclic graph. This is the definition of tree. This is the definition of tree. Yes or no? Now you can easily see in a tree, the number of edges is fixed. No maximum, no minimum. Yes or no? So this will always be, whether you take maximum minimum, the answer will be n minus 1. Tell me the answer for this question. What is the number of edges in connected graph on n vertices? Can you tell me what will be the number of edges in a connected graph on n vertices? I can say it will be greater than or equal to n minus 1. Yes or no? Okay, very simple. So the answer will be greater than equal to n minus 1. What are the number of edges in a connected graph on n vertices? So it will be greater than or equal to n minus 1. I hope you understood. Okay. Next, let's see. What is the number of edges in acyclic graph forest on n vertices? Tell me. In a acyclic graph, what you can say about the number of edges? I can say it will be maximum n minus 1. Okay, I can say less than equal to n minus 1. Okay, is this clear? Yes, 0 to n minus 1. Very good. Okay, the answer will be 0 to n minus 1. If you have a forest, in a forest, remember, the number of edges will be 0 to n minus 1. And in the previous question, how many edges in the connected graph? So minimum will be n minus 1 to n minus 1 edges to maximum. How many edges can be there? Maximum number of edges can be, that will be nc2. Okay, because when every two vertices have edge, so you can see this will be the range of number of edges in the connected graph, and you can see this is the range of number of edges in the forest. Tell me the answer for this question. Is it possible a tree with 9 vertices and sum of degrees of all the vertices is 18? Is this possible? This is not possible. Why? What are the reason? Can anyone tell me? See, if you have a tree with 9 vertices, then how many edges will be there? Let me know. How many number of edges? So you can see number of edges will be 8. Number of edges will be n minus 1. So that will be 8. Now you tell me what will be the total degree, means summation of degree of all the vertices. So you tell me what is the summation of degree of all the vertices in a tree. That will be twice the number of edges, and that will be 2 multiplied by 8. That will be 16. Okay, so can it be 18? The answer is no. Okay, this is never possible. I hope you understood. So very simple questions you can easily solve. Tell me the answer for this question. Is it possible that you have 9 vertices, 9 edges, and there is no cycle? We have 9 vertices, 9 edges, and there is no cycle. Is this possible? The answer, this is no. This is not possible. What is the reason? Can anyone tell me? Tell me. What is the reason? Because remember, no cycle means acyclic. See, no cycle means acyclic. This you already know. No cycle means acyclic. And in the acyclic graph, on n vertices, maximum how many edges you can put? Maximum number of edges that you can put. Tell me. We have already seen this. In acyclic graph, on n vertices, maximum how many edges you can put? That will be n minus 1. So is it possible that in acyclic graph you have 9 vertices, 9 edges? This is not possible. I hope you understood. Okay, just apply the concept. Nothing complicated. Tell me the answer for this question. Is it possible that you have graph with 8 vertices, 7 edges, and there is no cycle? 8 vertices, 7 edges, and there is no cycle. Yes, this is possible. Okay, simply it will be a tree. Yes or no? 8 vertices, 7 edges, there is no cycle. This graph actually will be a tree on 8 vertices. Yes or no? This graph will be a tree on 8 vertices. Okay, let's move on now. Now let's see this theorem. If a graph has n vertices and there are at least n edges, then it contains a cycle. Is this true? We have already seen this is true. Okay, because see, this is saying if a graph has n vertices and there are at least n edges, we have at least n edges, then is it possible it can be acyclic? Is it possible? It cannot be acyclic, right? Because if it is acyclic, then maximum how many edges I can have? In a acyclic graph, maximum number of edges, how many? Maximum number of edges can be n minus 1. Yes or no? So remember, if you have n vertices and at least n edges, then you cannot have acyclic graph, because acyclic graph has maximum these many edges. In a acyclic graph, maximum you can put n minus 1 edges. So if you have at least n edges, then definitely it contains a cycle. So this is very simple result. So you can easily see the proof is like this. If a graph has n vertices and at least n edges, then it contains a cycle. The proof is very simple, because if you do not want a cycle, then you want acyclic graph. Yes or no? If you want acyclic graph, then maximum n minus 1 edges you can put. So if you have at least n edges, then definitely there is a cycle. Definitely G is cyclic. Very easy to prove. Tell me the answer for this GATE 2014 question. The same question came in 1992. If G is a forest with n vertices, k connected components, then how many edges are there in this graph? The same question came in 1992. How many edges are there in a forest with p components on n vertices? So let's solve it. See, you have a forest. The question is saying that there is a forest. Forest means acyclic graph. In forest, tell me, every connected component is a tree, right? Yes or no? Because forest is a acyclic graph, so in this forest every connected component will be a tree. So you have a forest on n vertices and there are k connected components. Now we need to find how many edges are there. So what I can do, in this forest you have total n vertices and there are k connected component. The question is saying that there are k connected components. This we already know that in a forest every connected component is a tree, because what is a forest? That is basically a collection of trees, I can say. Okay, so forest means acyclic graph, so every connected component will be a tree. So you can see here these are the k connected components. So let me write it. For example, let's assume this is connected component C1, C2, C3, and so on Ck. These are the connected components. Now, I don't know how many vertices are there. Yes or no? In this component, how many vertices are there? I don't know. Okay, so let me assume that there are n1 vertices. Okay, let me assume that there are n1 vertices in this C1, and in this let's assume that you have n2 vertices, here you have n3 vertices, and here you have nk vertices. Tell me what are the total? N1 plus n2 plus nk, what are the total? The total will be n. Yes or no? Okay, you can easily see. So the total is going to be n. Now you tell me, this will be a tree? Yes or no? This will be a tree, because in a forest every connected component is a tree. Do you agree? Because forest is acyclic graph, so every connected component inside that forest, every connected component, that will be a tree. So you can see all these connected components, these are trees. Now you tell me, this is a tree which has n1 vertices. So how many edges will be there? What will be the number of edges? That will be n1 minus 1, these many edges. Okay, how many edges here? That will be n2 minus 1 edges. Okay, similarly, and so on. Here, how many edges will be there? That will be nk minus 1 edges. Okay, so very simple. Now you tell me, what will be the total number of edges? Because the question is asking how many edges are there. So what will be the total number of edges? So you can see number of edges, that will be this plus this and so on this. So you can see it will be n1 minus 1, n1 minus 1 plus n2 minus 1 and so on nk minus 1. Okay, so you can take all these n1 plus n2 plus nk, all these you can take together, minus how many times I will minus? You can see there are total k terms. Yes or no? So I will do minus k, because minus 1 minus 1 minus 1. So or ultimately it will become minus k, because there are total k terms. So you can easily see. Now what this n1 plus n2 plus nk, this will be the total number of vertices. So your final answer will be what? That will be n minus k. Okay, is this clear? So remember, in a forest, if you have k connected component, then number of edges will be n minus k. Okay, the same question came in 1992 and the answer will be n minus k, n minus p, because here you have p components. So the answer will be n minus p. Okay, very easy to prove, right? All you have to understand is that, see, forest is a acyclic graph. So in forest every connected component will be a tree. So what you do, the question is saying there are k connected components. So let's assume these are the connected components C1, C2, Ck. Now here I am assuming n1 vertices, here n2 vertices and so on. Okay, now because this is a tree, every connected component in a forest is a tree, so there will be n these many edges, n1 minus 1, these many edges will be there. So and so on. So you can see every connected component, number of edges you can find, and then total number of edges you can easily do the summation. So finally your answer will be n minus k. Tell me the answer for gate 1995. The minimum number of edges in a connected cyclic graph on n vertices, what that will be? We want connected graph which has a cycle on n vertices. So what the minimum number of edges we need to put? That will be n. Okay, because remember, if you have a connected graph with n minus 1 edges, that will be a tree, and tree does not have a cycle. Okay, yes or no? So remember, if you want a connected graph with a cycle, then minimum n edges you have to put. The answer will be option B. Tell me the answer for gate 1993 question. Consider a simple connected graph. Consider a simple connected graph on n vertices, and there are n edges where n is greater than 2. Then which of the following statement are true? G has no cycle. Is it necessary? See, the question is saying there are n vertices, n edges. We have n vertices, n edges. Then you tell me. We have already seen that if you have n vertices, n edges, and in a connected graph, if you have n edges, then definitely there will be cycle. Yes or no? So remember, option C is correct. That G has at least one cycle. Okay, is this clear? G has at least one cycle. This is definitely correct because remember, connected graph with n edges. That means there is a cycle. Okay, yes or no? Connected graph with n edges, that will be cyclic. So there will be at least one cycle. That is correct. Okay. Also, let's see the option A. Is it necessary? Is it necessary to be true? This is saying G has no cycle. This is never true. Yes or no? Because connected graph with n edges, that will definitely have a cycle. What about option B? The graph obtaining by removing any edge is not connected. The graph obtained by removing any edge is not connected. This is also not true. I can give you a counter example. Consider this A, B, C, D. Here you can easily notice that number of vertices is 4, number of edges is 4, and this is connected also. Okay. Here you can easily see whatever edge you remove. If I remove one edge, then what will happen? If I remove one edge, tell me. If I remove one edge, then also I will get a connected graph. Then also I will get a connected graph. That is the reason I can say this is the counter example for option B. Option B is gone. What about option D? The graph obtained by removing any two edges is not connected. Yes, this statement is true. What is the reason? Tell me. See, very simple point. In this here, you already have n edges. Okay, you have already have n edges, n vertices, and there is connected. Okay, this situation we already have. Tell me, if I remove two edges, then what will happen? If I remove two edges, then what will happen? Let me know. Remove two edges. If I remove two edges, then there will be n minus 2 edges. And there are n vertices. So can it be connected? Can it be connected? If you have n minus 2 edges and n vertices, can it be connected? So it will be not connected. Definitely it will be not connected. Because remember, minimally connected graph is a tree. Okay, and remember every tree has n minus 1 vertices. So if you want to create a connected graph with minimum number of edges, then you need n minus 1 edges. Okay, is this clear? So very simple point, if you want to create connected graph with minimum number of edges, then also you need n minus 1 edges. So if you have n minus 2 edges, then definitely it is not connected. Yes or no? So the answer for this question will be option C comma D. Okay, is this clear? Option C comma D, this will be the answer. Now actually one more point I want to tell you, a very interesting point. In this same question you tell me, if you have n vertices, n edges, and option C is saying that G has at least one cycle. That is correct. G will have at least one cycle. But how many cycle it will have? G will have at least one cycle. That is correct. But how many cycle G will have? Let me know. Yes, answer will be 1. G will have only one cycle. This is the interesting point you can see. In a tree, if you add one more edge between existing vertices, then it will create exactly one cycle. Do you agree with me? Okay, take any tree. For example, A, B, C, D, E. Okay, any tree you take. Now you can easily see if I add any edge between the existing vertices, this is the tree. In this tree, if I add, for example, this edge, then one cycle I will get. If I add this edge, one cycle I will get. If I add this, one cycle I will get. If I add this one cycle, I will get. Okay, so please understand, it creates exactly one cycle. The answer will be, this will be true. Okay, so in a tree, if you add one edge, if you add one edge, then remember result will be cyclic graph with one cycle. The graph will be cyclic with exactly one cycle. Tell me the answer for GATE 2004 question. What the maximum number of edges in cyclic undirected graph with n vertices? I told you that acyclic graph with maximum number of edges, that is the tree. And in a tree, how many edges you have? That will be n minus 1. So answer will be option A. Tell me the answer for this question. The minimum number of possible edges in an undirected graph with n vertices and n m components. You have undirected graph with n vertices are there, m components are there, and I want minimum number of edges, minimum possible number of edges. Then what will be the answer? So first of all, you tell me, if I want minimum possible number of edges, then definitely I will create acyclic graph. Yes or no? Do you agree that if I want minimum possible number of edges, okay, if I want minimum possible number of edges, then definitely what I will do, I will create acyclic graph. Okay, now what you are doing, you are creating acyclic graph where there are m components. Okay, so let me write, for example, these are the components, like this is component 1, component 2, component 3, and there are m components. I don't know how many vertices are there in these components. For example, maybe let's assume there are n1 vertices in this component, and let's assume there are n2 vertices in this component, and so on. There are n m vertices in this component. Okay, now you tell me. So you can easily see we have total m components. Okay, and the question is asking that minimum number of possible edges. Okay, so you can easily see, if I want to create a minimum number of possible edges, then I will create this to be tree. Yes or no? This also will be a tree. So every component will be a tree. Now you can easily see that total number of edges, what that will be, because here there will be these many edges. Number of edges will be these many. Here n2 minus 1, these many edges. And here n m minus 1, these many edges. If you do the total, then you will get n minus m. Okay, is this clear? If you do the total, like for example, number of edges, if you do the total, then you will get, you can see it will be n minus m. Okay, these many edges will be there. So very easily you can do this. I hope you understood. Let's see. Let's solve GATE 2010 question. So graph G, V, comma E, this is given to you. The question is defining this parameter, and this is summation of ID multiplied by D, where D is the degree and ID is the number of vertices of degree D. If S comma T are two different trees with, then what will happen? First of all, you try to understand what is this parameter. Look at this equation, and can anyone tell me what is this equation? See, this equation is simply telling you, here in this equation, what we are doing, ID is the number of vertices of degree D. Means for every degree D, this is what you are doing. Please understand here. For every degree, we are multiplying with the number of vertices of that degree, and then we are doing the summation. For every degree, we are multiplying with number of vertices of that degree, and then we are doing summation. So this is what you are doing. For every degree D, for every degree, for example, this degree, then this degree you are multiplying with number of vertices of degree D3, like this, and then you are doing the summation. So if you do this, then it is basically what? This is basically your degree summation. Yes or no? This is basically the total degree, which is equal to twice the number of edges. This we already know. Okay, so you can easily see that this parameter that is given to you, this equation that is given to you, this is just a degree summation. Okay, this is just a total degree of the graph. Now the question is saying that S comma T are tree. This S is a tree and this T is a tree. Okay, where the total degree is same. The question is saying that both have same total degree. Okay, so you can see Let's assume in this let's assume the number of vertices is n1. Okay, let's assume these many vertices I have here, and here let's assume the number of vertices is n2. Then tell me, what will be the total degree? Total degree is already same. You know the total degree will be equal to twice the number of edges. So here I can say that twice the number of edges here is equal to twice the number of edges here. Okay, and what are the number of edges here in this S? That will be 2 into n1 minus 1. This will be equal to 2 into n2 minus 1. Okay, because remember, if you have n2 vertices in a tree, then that simply means there are n2 minus 1 edges. Okay, so you can see in the question it is saying that total degree is equal. Total degree is same. Total degree is equal to twice the number of edges. So you can see 2 into number of edges is n1 minus 1, and here number of edges is n2 minus 1. So from here you can see that it will be n1 equal to n2. Okay, so this is what you got. Finally, we got n1 equal to n2. Means number of vertices in both the trees will be same. So you can easily see number of vertices in S equal to number of vertices in T. Okay, so for this question, the answer will be option C. Very easy, not a complicated question. Let's solve one question for the future GATE exam. This question has not come in the GATE exam so far, and definitely someday it will come in the GATE exam. So let's see this question for the future GATE exam. A graph with n vertices, m edges has minimum how many connected components? A very basic question. You have a graph where there are n vertices and there are m edges. Now, minimum how many connected components will be there? We want smallest number of connected components with n vertices and m edges. Let's see in the GATE exam if this question comes, then how you will solve? Very easily you can just take some values and you can try to create minimum number of components, yes or no. So let me take number of vertices equal to 6 and number of edges equal to 3. Okay, so tell me minimum how many components you can create, let me know. Okay, in this situation, number of vertices 6, number of edges 3. Let's try to create smallest number of connected components. Try to create smallest number of connected components. So remember, you have 6 vertices A, B, C, D, E, D, E, F. These are the vertices, and you have 3 edges. Let's try to create minimum number of connected components. So let me put this as okay. Now here let me put for example, let me put this as and let me put this as. Tell me how many components I got. If I do like this, then how many components I got here? If I do like this, I got total 4 components. Yes or no? Can I do better than this? Means can I get smaller number of components? I want to get minimum number of components. Please understand. I want to get smallest number of connected components. So can I do better than this? Yes, of course I can do better than this. Please understand. See. Why are you putting this cyclic as? Yes or no? Why are you creating this cycle? Instead of creating this cycle, you can use this as and you can reduce the number of components. Do you agree with me? Just use common sense. Why are you creating a cycle? Okay, instead of creating a cycle, use this as and reduce the number of components. Okay, so this is what I am saying, that the best way is A, B, C, D, E, F. Don't create a cycle. Do not create a cycle, because remember, I want smallest number of connected components. Okay, so what I will do, every edge I will use to reduce the number of components. I hope you understood. So what I will do, okay, I will put this as, I can put this as, I can put this as. Now you can easily see how many components I got. 1, 2, 3. So 3 components I got. Now let me tell you, whatever you do, you cannot do better than this. This is the minimum number of components you will get. Okay, you cannot do anything better than this. For example, if you do like this, one is here, one is here, and let's assume one is here, then also no problem. Okay, here also how many components you got? Tell me. Here also you got 3 components. Okay, are you getting my point? So I am saying that the minimum number of components you will get here in this situation, that is 3. Okay, in this situation, smallest number of components, minimum number of components that you will get, that will be 3. Okay, is this clear? Let me give you one more scenario. For example, let's assume that number of vertices is 4, and let's assume number of So number of vertices is 7, and let's assume number of edges is 4. Now you tell me, in this situation, I want minimum number of connected components. So what that will be? Again, very simple. A, B, C, D, E, F, G. So these are the 7 vertices. Now you tell me, there are 4 edges. Okay, so what I can do? I can put this as, I can put this as, I can put this as. Tell me, if I do like this, then how many components I got? Here how many components? Here I got total 4 components. Yes or no? Here I got 4 components. But you tell me, here did you notice one thing? Why I am putting this cycle? Instead of putting this cycle, I can use this as to reduce the number of components. Do you agree with me? This is just a common sense. It is not a complicated question. Just use your common sense. Why are you creating a cycle here in this graph? Why are you creating a cycle? Okay, instead of creating a cycle, this is I can use to create this is I can use to reduce the number of components. So what I can do instead, instead of making this a cycle, okay, I can use this age to reduce the number of components. Okay, so for example, I can do this. Now you can see how many components I got. So now I got 3 components. Okay, did you understand? Now whatever you do, for example, if you do like this, then also you will get for 3 components only. Okay, you can do, as long as you are not creating a cycle. Please understand, as long as you are not creating a cycle, whatever you do, you will get same number of components. So again, you got 3 components. So are you getting my are you getting the idea? What the answer? Are you getting the idea that if you have n edges, n vertices, m edges, then smallest number of components what you will get? I think you are getting the idea. That will be n minus m. Okay, this is the smallest number of components you will get. I hope you understood this. Okay, so very simple. Now, now let me prove it also. But I hope you got the answer. See, in the GATE exam, can you get the answer if this question comes? Let's assume you don't know the proof. Then can you get the answer in the GATE exam? Yes, of course you can get the answer. You can just create like this. I have done. Okay, you can take values n comma m, and then you can you can get the answer. But let's see the proof also. Actually, the proof is very cute. That is the reason. Let's see the proof also. Okay, so this is the theorem. A graph with n vertices, m edges has at least n minus m connected components. Means if you have n vertices, m edges, then minimum, remember, smallest number of components will be n minus m. At least these many connected components will be there. Okay, and the proof is actually very cute proof. So let's see the proof. This is the idea, this is the observation you need to make to prove this result. If you want to prove it, then just make a small observation that in any graph, if you add one edge, then adding one edge can change the number of components by how much? Can you tell me? Just visualize. Okay, just think about it. In a graph, if you add one edge, I am adding one edge, then can the number of components increase? Can it happen? A common sense question I am asking. Can it happen? In a graph, I am adding one edge, then it can it happen that number of components are increasing? No, it cannot happen. Number of components cannot increase if you add one edge. Okay, so what can happen then? If I add one edge, then remember, the number of components can reduce, or the number of components can remain unchanged. Okay, let me take one example. Consider this graph: a, b, c, d, e, f, okay, g, h, g, h, I, j, k. Okay, so like this. So let's assume this is the graph here. This thing is the graph. Okay, this is your graph g. Now you tell me, in this graph g, here, if you add one edge, I am adding one edge, then tell me, for example, if I add bf, if this edge I add, then tell me what will happen. If I add this edge, then number of components, how it will change? Can anyone tell me? By adding this edge, I am adding this edge, the number of components will change by how much? Unchanged. Yes or no? So you can see unchanged. Unchanged number of components. Okay. Now you tell me, instead of adding this age, if I add, for example, fh, if I add this age, this fh, then tell me, then number of components will reduce by one. Yes or no? Is this clear? Number of components reduce by one. Okay, is it possible that number of components can increase? Is it possible if I add one age, for example, if I add, then is it possible that number of components can increase? It can never happen, never. Okay, if you add one age in this graph, if you add one age, the number of components can never increase. Is it possible that number of components can decrease by two? See, if I add one age, I am adding one age, then is it possible that number of components can decrease by two? It also cannot happen, because if I add one age, then maximum one reducement can happen. Yes or no? One component can reduce. Because if I add one age, then two components can merge, then one component is reducing. Just think about it. It is just a common sense. Just visualize this. You have, let's assume there are 10 components. Think about it. There are 10 components. Now if you add one age, then it can happen that two components can merge, so total one component is reducing. Yes or no? Are you getting my point? This is just a common sense. Visualize in your mind. If there are 10 components, you are adding one age, then what can happen? Two components can merge. Then total number of components will decrease by one. So either the total number of components will reduce by one, or it will remain unchanged. Yes or no? So this is the simple observation you have to make. Finally, I can say, in any graph, if you add one age, then either the number of components will reduce by one, or the number of components will remain unchanged. Please tell me, did you understand this? Let me know. So very simple. You can see, in any graph, adding one age can reduce the number of components by at most one. Okay. So after making this observation, now you can easily prove. So you can easily see that. Now tell me one thing. I am already saying that if you add one age, then number of components can reduce by maximum one. Yes or no? Now you tell me, if there are, let's assume, n vertices. Just think about it and tell me. And let's assume there are five edges. Okay, there are n vertices, there are five edges. Now you tell me, I told you that in any graph, if you add one edge, the number of components can reduce by at most one. Either the number of components will remain unchanged, or the number of components will reduce by one. Okay, so if I want minimum number of smallest number of components, then what should happen? My target is, this is what I want. I want smallest number of components. I want smallest number of components. Then what should happen? Tell me simple point. I want smallest number of components. Then what should happen? Then every edge should reduce number of components by one. Yes or no? Because every edge can reduce the number of components by at most one. Okay, because of any edge, either the number of components will not change, or the number of components can reduce by one. Now if I want smallest number of components, then what should happen? Every edge should reduce the number of components by one. Do you agree with me? So I am saying, if there are n vertices and there are five edges, and I want smallest number of components, this is what I want. I want the minimum number of components. Then what should happen? Every edge should reduce the number of components by one. So initially when you have n vertices, then how many components are there? Initially when you have n vertices, then there are n components. Initially, let's assume there is no edge. Okay, see, very simple point. Initially, this is the situation. Initially you have n vertices and there are n components. Okay, there are n components, right? There are n vertices, n components. Now what I am doing? Now I am adding five edges. Now I am adding five edges. Now you tell me, initially there is no edge, so there are n vertices, all are isolated vertices, so there are n components. Now I am adding five edges. Then what I will do? If I want smallest number of components, then because of every edge, the number of components should reduce by one. Okay, what any edge can do? Just think about it. Any edge can reduce the number of components by at most one. Okay, so what I will do, if I want smallest number of components, then every edge will reduce the number of components by one. So if there are five edges I am adding, so number of components can reduce by five. Yes or no? This is what they can do. This is what these edges can do. So very simple. Okay, initially there is no edge, so there are n components. If I add 5 edges, then smallest number of components that I will get, that will be n minus 5. Okay, I hope you understood this point. Okay, so this is the simple proof. Did you understand this simple? Tell me, did you find this proof simple? This was just a cute proof. All you have to do, just think about that in any graph, if you add one edge, if you add one edge, then what will happen to the number of components? You can see if you add one edge, the number of components can reduce by at most one. Either the number of components will remain unchanged or the number of components will reduce by one. Okay, so very simple point. Let's assume initially there is no edge. Initially, all the vertices are isolated vertices, so there are n components. Now, if I add, for example, let's assume if I add six edges, then what these six edges can do? They can reduce the number of components by at most one. But I want minimum number of components. This is what I want. I want minimum number of components. So what should happen? So these edges should reduce the number of components by one. Each edge, every edge should reduce the number of components by one. So finally, if I add six edges, the number of components should reduce by six. So finally, minimum number of components that I will get, that will be n minus 6. This is the simple proof. I hope you understood. So you can easily see that initially you assume that there is no edge. Okay, this proof I've written here, please read this, that initially assume there is no edge, so n vertices have n components. If every edge is reducing the number of components by 1, then I will get the minimum number of components, that will be n minus m. So that's it. This is the proof, and this is the theorem for the future gate exam. Basically, in the future gate exam, they can create a MCQ question, and they can ask you, for example, they can give you that, okay, there are n vertices and there are m edges, then minimum number of components will be how much? Option A, option B, option C, option D. And this option, let's assume there is this option, so this will be the correct answer. Okay, did you understand? Please tell me. If you have n vertices, m edges, and minimum number of components will be n minus m. This is the smallest number of components that you can have. So you can see a graph with n vertices and m edges has at least minimum these many connected components, at least n minus m connected components. Okay. Let me give you one more small observation. Just make one more small observation. That is, if you have a graph with n vertices, m edges, then you already know that minimum these many connected components we can have. Okay, so see, look at this. If you have n vertices and there are m edges, okay, this we already know that in this situation, what are the smallest number of components we can have? What are the smallest number of components? That will be n minus m. You just tell me simple point. To create these smallest number of components, will you put a cyclic edge? Will you create a cycle? This we have already seen, if you remember. See, if you have n vertices, m edges, then we already know that minimum number of components will be these many. These many are the minimum number of components. But to create these minimum number of components, are you sure that every component will be a forest? Every component will be a tree? Or I can say that basically it will be acyclic. Yes or no? The graph will be acyclic. Do you agree? Okay, so this is the point. This is the point. Simple point. Remember, if you have n vertices, m edges, then minimum, the smallest number of components we can have is this. Okay, and this type of graph, which has minimum number of components, this type of graph will be acyclic. I hope you understood. We have already seen this. Okay, okay, just I can say 5 or 10 minutes ago, we have already seen this, that if you have n vertices, m edges, and if you try to create minimum number of components, if you try to create smallest number of components, if you try to create, then you will never put cycle. Yes or no? Then your graph will be acyclic if you want to create minimum number of components. So this is what I'm saying, that any graph with n vertices, m edges, and minimum number of components will be a acyclic graph, will be a forest. Okay, it will be a forest. So that's it. So this is the variation of the theorem for the future gate exam, remember. So this is just a small variation. It is nothing complicated. This is just a small variation, that every graph with n vertices, m edges, and n minus m connected components, because this is the minimum number of connected component possible. Yes or no? This is the minimum number of connected component possible. So if your graph has these many connected component, then it will be a forest. Okay, clear? Let me know. So this this theorem, this simple theorem and its variation are both clear? Let me know. These are the questions for the future gate exam. Now we will study the next topic, that is planar graph. Our next topic is planar graphs. What is a planar graph? First, you understand what is edge crossing in a 2D diagram. On a 2D plane, like your paper, on paper, when you draw a graph, then when can I say two edges are crossing? The name itself is telling you edge crossing on the 2D diagram. So let's assume there are two edges, E1, E2. So when can I say two edges are crossing in a diagram? Very simple. If this type of situation happens in the diagram, that these two edges, these are basically crossing each other on the paper, yes or no? On the 2D plane, on the 2D paper, these two edges are crossing each other. This is called drawing with edge crossing. Is this clear? Whenever you draw a graph with this type of edge crossing, then this will be called drawing with edge crossing. That you are drawing the graph with edge crossing, drawing with edge crossing. Is this clear? So this is the property of graph, or is this the property of drawing? Let me know. This is the property of drawing. Basically, you are drawing the graph with edge crossing. Okay, is this point clear? Very simple point. Now let's see the definition of planar graph. A graph is planar graph if there is some way to draw the graph without edge crossing. Please read this statement. What is the definition of planar graph? A graph is planar. A graph is planar if there is some way, if this graph you can draw on the 2D plane, if there is some way without edge crossing you can draw. This is the definition of planar graph. For example, look at this graph and tell me, is this planar graph? This graph, is it planar graph? Yes, this is planar graph. Please focus on the definition. A graph is planar if there is some way to draw the graph without edge crossing. This graph, can you draw without edge crossing? See, this drawing has edge crossing, but can you draw this graph without edge crossing? Please understand. I know this diagram, or I can say this drawing has edge crossing, but read the definition of the planar graph. A graph is planar graph if there is some way to draw this graph without edge crossing. So can you draw this graph without edge crossing? Yes, I can do that. Okay, what I can do? This graph we can draw without edge crossing like this. Okay, I can do. That's it. So remember, is this planar graph? Your answer will be what? Your answer will be yes. Please understand. Yes, this graph is planar graph. Look at this graph. This graph is planar graph. Okay, why this graph is planar graph? Because there is some way to draw this without edge crossing. This is very important. Many students, they don't understand this simple point that, see, this drawing has edge crossing, but I am saying the graph is planar if there is some way to draw this graph without edge crossing. You can see this graph I can draw without edge crossing. You can see there is no edge crossing in this diagram. In this drawing, there is no edge crossing. So I can say this graph is planar graph. Okay, is this point clear? So is this graph planar? The answer is yes. So this is the definition of planar graph, and this is very important. A graph is planar if there is some way to draw the graph without edge crossing on the 2D plane. What about this graph? Is this graph planar graph? Remember, this drawing has edge crossing. Yes or no? In this drawing, you see this edge they are crossing. So in this drawing, for example, look at this edge. Also look at this edge. So they are crossing. So remember, in this drawing there is edge crossing. But I am asking, is this graph planar graph? Can you draw this graph without edge crossing? The answer is yes. So remember, this graph is planar. The answer is yes, because what I can do, I can draw this graph without edge crossing. See this, what I am going to do. I can draw this graph very easily like this. That's it. Now you can see this is the drawing without edge crossing. Okay, is this clear? So remember, is this graph planar graph? The answer is yes. But remember, in this drawing there is edge crossing. In this drawing there is no edge crossing. They are same graph. They are same graph. Okay, so this graph is planar graph because I can draw this graph without edge crossing. Okay, so you can easily see. So remember, this graph is a planar graph. This graph is a planar graph. The reason is very simple, because I can draw this graph without edge crossing. Tell me the answer for this question. Two graphs are shown below. Which of them is planar? The options are which of them is planar. So you can easily see that this graph is also planar, this graph is also planar. We have already seen. Is this graph planar? K2n, complete bipartite graph. One part has two vertices, another part has n vertices. Is this graph planar graph? Let me know. K2n. For example, what about K24? Let me know. K24. Okay, K24 means one part has two vertices and another part has four vertices. So tell me, this K24, is this planar graph? K24 means complete bipartite graph. Yes or no? One part has two vertices, another part has four vertices. So you can see this is K24. So tell me, is this planar graph? Is this graph planar graph? See, this drawing is not planar. I can say this drawing has edge crossing, but can you draw this graph without edge crossing? Can you tell me? Is it possible that you can draw this graph without edge crossing? Is it possible? Just be clever. Okay, use your brain. Be clever. Can you draw this graph without edge crossing? Yes, of course, I can draw this graph without edge crossing. See what I can do. These four vertices are there. One vertex I will put here, one vertex I will put here. Okay, is this clear? That's it. Now you can see this is the graph I will get. Is this clear? So you can see, yes, this is a planar graph. Is this planar graph? The answer is yes. Please tell me, did you understand? So remember, planar graph means a graph which you can draw. There is some way to draw without edge crossing. So you can see this K to N. This is a planar. Okay, understood? Let's solve this GATE 2005 question. Which of the following graphs are planar graph? Three graphs are given to you. Which of them are planar? Let's see one by one. What about G2? Is this graph planar? Yes, of course, this graph is planar. Yes, this graph is planar, because what I can do, I can draw this graph without edge crossing. Okay, see what I can do. This is what we can do. Okay, here this edge I can put here like this. Okay, do you agree with me? So you can see, yes, this is a planar graph because I can represent this graph without edge crossing. Tell me about this graph. Is this graph planar graph? Again, the answer is yes. This is also planar graph because I can represent this graph. I can draw this graph without edge crossing. Okay, see what I will do. Without edge crossing, I need to draw this graph. Can I draw? Can you draw without edge crossing? Yes, of course I can draw. What I will do, notice this edge I will put like this. Okay, so you can see this graph is also planar graph. Understood? Please tell me. Very simple, right? Okay, what about this? Is this graph planar graph? Yes, this is also planar graph. Here you can easily create the planar representation. Basically, you can create a diagram without any edge crossing. Okay, so let me create. So these are the five vertices. I can create the diagram without edge crossing. See what I can do. I can put this edge, I can put this edge, and then here. So let's see how to create the drawing without edge crossing. Okay, see. So this is what I can do next. See these edges, you can see this edge and this edge, they are not crossing each other. So I can put like this, and you can see that this edge, yes, this edge I can put here, and also which edge is missing now? This edge. Okay, so this edge I can put here. That's it. So you can easily see. So okay, this graph, remember, this graph I can draw without edge crossing. So this is also planar graph. I hope you understood. So in this diagram, remember, which is a planar graph. This is planar, this is planar, this is planar. So did you understand? Remember, this drawing has edge crossing, but I can draw the same graph without edge crossing. I can draw the same graph without edge crossing. I can draw the same graph without edge crossing. So they are planar graph. So remember the definition of planar graph. Again, I am telling you, planar graph means there is some way to draw the graph without edge crossing. Okay, this is the definition of planar graph. Tell me the answer for this question. Is there any graph which cannot be drawn without edge crossing? You might be thinking, so far all the graph that we have seen, we can draw them without edge crossing on the 2D plane. On the 2D paper, I can draw them without edge crossing. So is there any graph which you can never draw without edge crossing on the 2D plane? Means, is there any non-planar graph? So let me tell you the answer. Yes. The answer is K5 and K33. Okay, these are the most popular examples of non-planar graph. K5, complete graph on 5 vertices, also K33, that is complete bipartite graph K33. So you can see these two graphs, if you try to draw them on the 2D paper without edge crossing, it is never possible. Okay, is this point clear? So please understand that this K33, this is complete bipartite graph K33. This is not planar, means there is no way, read this, there is no way to draw this graph on the 2D paper without edge crossing. Okay, so this is what I'm saying. Is there any graph which you can never draw without edge crossing? The answer is yes. K3, K33 and K5. These are the most popular examples. Okay, so these are non-planar graph, means these graphs I can never draw without edge crossing. Whatever drawing I make, that will have edge crossing. So these are non-planar graph. So did you understand the definition of planar graph and non-planar graph? Planar graph means there is some way to draw without edge crossing, and non-planar graph means there is no way to draw without edge crossing. Now let's see the next topic, that is planar representation or planar embedding. So let me tell you the definition. Planar representation, the name itself is telling you that it is just a representation. So if you have a planar graph, then planar representation is the representation without edge crossing. I can say for any planar graph, what is a planar embedding? What is planar representation? That is the drawing without crossing edges. Okay, is this clear? Any drawing without edge crossing, that is the planar representation of a planar graph. For example, consider this K4. Okay, for this K4, I can draw this K4 like this. Tell me, is this a planar representation? Look at this drawing. Okay, let me call it drawing D1. Is this planar representation? This is not a planar representation. Yes or no? This drawing is not a planar representation of K4. Okay, because remember, planar representation means drawing without edge crossing. So you already know this is a planar graph. This we have already seen that this K4 complete graph on 4 vertices, this is a planar graph, but this drawing is not a planar representation. I can create a planar representation. Remember what I can do? I can do like this. I can do like this. Now you can see this is a planar representation. Okay, is this clear? This diagram, this is a planar representation of K4. Is there any other planar representation of K4? Can you give me some other planar representation of K4? Yes, of course. Look at this. Let me give you one more. Okay, see, consider this. This is another planar representation of K4. This is also planar representation of K4. Okay, can you give me another planar representation of K4? Yes, of course, I can give you. For example, consider this. You have this triangle, and then let me put vertex here. Okay, so like this. So you can easily see this is also planar representation of K4. I hope you understood. So very simple, just read the definition. If G is any planar graph, means you can draw this graph without edge crossing on the 2D paper. Yes or no? There is some way, there is at least one way to draw this graph on the 2D paper without edge crossing. Now, what is planar representation of a planar graph? Planar representation means drawing without edge crossing. Okay, so remember, K4 is planar graph, we already know. But you can see this drawing is not planar representation. This drawing is planar representation because this is drawing without edge crossing. You can see this is also planar representation. This is also planar representation, and this is also planar representation of K4. Okay, so we have seen that this drawing is not a planar representation, but this graph is planar graph. Please understand, this graph is planar graph. This graph is a planar graph because there is some way to draw this graph without edge crossing. Okay, but remember, this drawing is not planar representation. Okay, this drawing is not a planar representation. I hope you understood the difference. Understand the difference between planar graph and planar representation. You can see this drawing, this is not a planar representation, but this graph is planar graph because there is some way to draw this graph without edge crossing. Let's see this note. A graph is planar graph if and only if there exists at least one planar representation. Yes or no? If you have a planar graph, then definitely some planar representation will be there. And if you have a planar representation, then it is a planar graph. So you can see a graph is planar graph if and only if there exists a planar representation for G. Tell me this, is this graph planar graph? The answer is yes. We have already seen this graph is planar graph, but remember this drawing is not planar representation of G. This drawing is not planar representation of G2. Okay. I can create a planar representation of G2. What that will be, for example, look at this. Like this, I can create the planar representation. Yes or no? Now this is the planar representation of G2. Okay, let's move on. So you can see any graph, we have already seen that any graph you can draw in many ways on the 2D plane. Yes or no? For example, this K4, this graph you can draw in many ways on the 2D plane. Now if your graph is planar graph, then there is at least one way to draw the graph on the 2D plane without edge crossing. Okay, but there can be more ways. See, if G is a planar graph, then any drawing without edge crossing, that is the planar representation. This definition we have already seen. Okay, now let's move on. Now let's see the next concept, that is face or region or in a planar representation. What is the concept of face? Remember, face or region both are same. So let's see this. Consider this K4. We have already seen K4 is a planar graph because there is some way to draw this graph without edge crossing. So K4 is planar graph. Consider any planar representation of K4. Remember, you can take any planar representation because remember, multiple planar representations are there. Do you agree with me? Okay, so what I'm doing, take any. For example, let me take this planar representation. Okay, now this is one of the planar representation of K4. So consider any planar representation of K4 like this you can consider. Now in this, what is the face? Let's see the face in a planar representation, or I can say region in a planar representation. So here let me tell you, this area surrounded by the edges, this is called face. Very simple definition. Look at this. This area is surrounded by edges. So this is called face. Let's call it face number 1. This area is surrounded by edges. This is face number 2. This area is surrounded by edges. This is a face number 3. And this outside area this is face number 4. Okay, is this clear? So this is the definition of face. I hope you understood this idea. Okay, so these are the faces. So in this planar representation, there are 4 faces. Is this point clear? In this planar representation, because consider this planar representation, then here you have total 4 faces. Okay, now let's see another planar representation of K4. Because K4 has many planar representations, what I can do, I can consider this planar representation. This is also K4. This is also planar representation. Now tell me how many faces I have. Again, you can notice this area surrounded by edges. This is face number 1. Area surrounded by edges. This is face number 2. Area surrounded by edges. This is face number 3. And this outside area, this is face number 4. Okay, so again, what you have, there are 4 faces. I hope you understood. Okay, very simple, right? Now let's move on. So let's see the definition of face. If you have any planar representation, this is very important point, that when you are finding face, or I can say region of a planar graph, then you have to consider planar representation. Okay, basically that drawing you have to consider which has no edge crossing. Okay, is this clear? So you can see in any planar representation, the area surrounded by edges or the outer area, that is the faces. Okay, is this clear? The area surrounded by edges or the outer area, okay, these are called the faces or regions of a graph. Consider this graph. Tell me, is this planar representation? Let me know. Is this a planar representation? Yes, This is a diagram without edge crossing. There is no edge crossing. Yes or no? So this is a planar representation. Yes or no? I can say this is a planar representation of graph G. This is already a planar representation. Now, how many faces are there? You can easily see this area surrounded by edges. This is face number one. Let me call it face number one. This area surrounded by edges. This is another face. This area surrounded by edges. This is another face. Okay. And you can see this area surrounded by edges, another face. And this outer area, this is another face, that is F5. Okay, is this clear? So total five faces are there. Remember, we have total five faces or five region. And remember here, how many outer area are there? How many outer area? Let me know. So you can see this is the outer area. There is only one outer area, or I can say there is only one outer face. This F5, this is called outer face. This is the outer face. Okay, is this clear? Very simple. You can call it outer face, or you can call it exterior face, or you can call it infinite face. Because remember, this is infinite face. Yes or no? This is infinite face. But remember, these are finite. Okay, yes or no? You can say this area, look at this area. This is a bounded area. So you can say that this is unbounded area. This is unbounded face. Okay, and these are bounded faces. For example, this is a bounded face. So total five faces are there. How many bounded face? How many unbounded face? Tell me. So you can see there is one unbounded face and there are four bounded faces. Please tell me, did you understand? Let me know. A student is asking, can we merge F1, F2? Okay, for example, this F1, this F2, can we merge F1, F2? The answer is no. See, face means area surrounded by edges. You can see this is the area surrounded by these edges. Okay, look at this. This one, this one, this one. So this is the area surrounded by edges. Now, if you merge, now you are basically, it's like you are crossing the edges. Okay, are you getting my point? You cannot cross a edge. You cannot cross this edge. For example, this is one face. This entire area is another face. This is another face. This is another face, and this outer area is another face. Okay, is this clear? In simple words, without crossing the edge, how much area you can cover? Are you getting my point? Please tell me. See, if I'm standing here, just think about it. If I'm standing here, then how much area can I cover without crossing edge? I cannot cross edge. So this is the area I can cover. I hope you understood. This is very intuitive concept. Is this point clear? See, if I give you any graph, consider this graph. Consider this graph. Here you can notice that if I am standing here, then how much area I can cover without crossing the edge? You can see this is the area. So you can see this is the face number one. Similarly, if I am standing here, then this is the area I can cover without crossing the edge. And this outer area I can cover without crossing the edge. So there are three faces here. Okay, is this clear? Please tell me. Did you understand? Now let's move on. For any planar graph, the number of unbounded faces that will always be one. Not more than one, not less than one. Is this clear? For any planar graph, the number of unbounded faces. I told you what is unbounded face. You can see this outside face. This is the unbounded face. So remember, in any planar graph, the number of unbounded faces is always one. Okay, let's move on. Tell me the answer for this question. Determine the number of faces in the planar graph. One thing, very important point I want to tell you. Before you find the number of faces, you just check, is this planar representation? Is this a drawing without edge crossing? Yes, this is a drawing without edge crossing. Now you can find the number of faces. You can see this is the area surrounded by edges. So this is the face. You can call it face number one. You can call it face two, face three. And this outside area, this is your face number four. So finally, the number of faces will be four. Okay, here remember this F4. What is this? This is your unbounded face. Okay, this is also called exterior face, or you can call it infinite face. Okay, and these are bounded faces. For example, this F3, this is bounded face. Let's move on. Now, let me tell you a very important note, because here you can make mistake. So, note is like this. If you have a planar graph, now if you want to find the number of faces in this graph, I give you a planar graph. In that graph, if you want to find the number of faces, then always consider a planar representation. Before finding the number of faces, first you consider the planar representation, means you consider drawing without edge crossing, and then you find the number of faces. Okay. For example, in this graph, first of all, you tell me, is this planar graph? Let me know. Is this graph planar graph? Yes, this is K4. We have already seen this is a planar graph. Now you tell me, what are the number of faces? What is the number of faces in this graph? Number of faces does this graph has? This is a planar graph, I already know. Yes, this is a planar graph. But how many faces are there? So can I say this is face number 1, face number 2, face number 3, face number 4, and outer face number 5? Can I say answer is 5? Let me know. Can I say answer will be 5? No, this is wrong. Why this is wrong? Because this is not the planar representation. Whenever you are finding faces, number of faces, then you always consider the planar representation. Okay, is this clear? Here you already have edge crossing. So first you create planar representation. You can create any planar representation. You don't have to worry about a particular planar representation, because remember, this is K4. You can create many different planar representations. You can consider any of them. Okay, any of them you can consider. For example, you can consider this one. No problem. Okay, any planar representation you can consider. Now you tell me how many faces are there. Now you can easily see face number 1, face number 2, face number 3, face number 4. So what will be the answer? The answer will be 4 faces. Okay, is this clear? So this graph, please understand, if someone asks you this graph has how many faces, your answer will be 4. Okay, so in this graph there are 4 faces. Is this point clear? So remember, for this graph I am asking how many faces are there. Then first you convert this into planar representation. Any planar representation you can consider. There can be many planar representation, but you can consider any of them. Okay, you don't have to worry about which planar representation to consider. No, you can consider any planar representation, and then you count the number of faces. You can see the number of faces here, that is 4. Okay, tell me, what are the number of faces in this graph? In this graph, how many faces I have? So first you consider the planar representation. This is not the planar representation. First you create a drawing without edge crossing. Okay, so let me create this drawing which is without edge crossing. Okay, now you can easily count the number of faces. You can see, for example, F1, F2, F3, F4, F5, and there is F6. So there will be total 6 faces. How many unbounded? This is one unbounded face and 5 bounded faces. Okay, is this point clear? So please tell me, if I ask you this graph has how many faces, then what your answer will be? What your answer will be? This graph. If I ask you this graph has how many faces, what your answer will be? That will be 6 faces. So this is a warning, you can see. In a standard book, this warning is given because they know that many students, they will make mistake. So remember, in any graph, if I ask you how many faces are there, then first you consider the planar representation. Okay, because if you find the number of faces in this drawing, if you find the number of faces, then the answer you will get, that will be 5. But in this drawing, if you find the number of faces, you will get only 4, and this is correct. The answer will be 4. Okay, the answer will be 4 faces. So this is a warning that in any graph, if I ask you how many faces are there, then first you create the planar representation. And remember, you can create any planar representation. You don't have to worry which planar representation to consider. No, you can create any planar representation of your choice, and then you can count the number of faces. Tell me number of faces in this diagram. This is a tree. This is a graph without any cycle. How many faces are there in this? Only one face is there, because remember, see, just think about it. If I'm standing here, then how much area I can cover without crossing the edges? See, without crossing the edges, I can cover the whole area. Yes or no? Without crossing the edges, whole area I can cover. So very simple. In this graph, tell me, in this tree, because this is a tree, so here how many faces are there? There is only one face, and that face is exterior or interior? That is bounded or unbounded? Tell me. There is only one face and that is also unbounded. So every tree is a planar graph. Do you agree with me? Okay, every tree is a planar graph and it has only one face, that is unbounded face. Very simple. Every tree, remember, every tree is a planar graph because every tree I can draw without edge crossing. Okay, on the 2D plane. So every tree is a planar graph with only one face, that will be unbounded face. Every forest is a planar graph with only one face. Yes or no? If I give you some forest, consider, for example, consider this forest. Tell me, how many faces are there? In this, how many faces are there? There is only one face. Yes or no? There is only one face. So very easily you can see that every forest is a planar graph with only one face and that is also unbounded face. In this graph, first of all you tell me, is this planar representation? Let me know on your screen. Is this planar representation? Yes, because there is no edge crossing. This is a graph drawing. This is a drawing without edge crossing. Tell me how many faces are there? Very easily you can find. See, area surrounded by edges. Let me call it F1. Let me call it 2. Let me call it 3, 4, 5, 6, 7. Okay, this area. This is 8. Yes or no? This area 8. Then there is 9. Then there is 10, 11. Okay, and there is 12. Yes or no? Outer area. So you can see number of faces will be 12. I hope you understood. Okay, there are 12 faces and where only one unbounded face is there. This is the unbounded face. So we have seen all these concepts. Tell me the answer for this question. Let G be a planar graph. Is planar representation unique? Is planar representation unique? The answer is no. We have already seen that for this K4. Consider this K4. For this, I can create many planar representation. For example, this is one of the planar representation I can create. I can create another. Consider this. Okay, consider I can create the planar representation like this. We have already seen. So remember, you can create many planar representation. Is the planar representation unique? The answer is no. I hope you understood. Okay, let's move on. Now, there is a curious question. You might be thinking, definitely some of you might be thinking that, sir, I have a planar graph, so I can create planar representation. That is fine. Okay, because planar graph means I can draw this graph without edge crossing. Okay, now we can get many planar representation. Yes or no? For this K4 complete graph on 4 vertices, for this we have many planar representations. Now you tell me, all these different planar representations, will they have same number of faces? This is a curious question or not? I told you, if a graph is given to you and they ask you how many faces are there in this graph, then what you do, you create any planar representation. You can create any planar representation and you can count number of faces. So you tell me, number of faces, does it depend on particular planar representation, or will it be same for all the planar representation of a graph? This is a curious question. I hope you are thinking that G is a planar graph, then G can have many planar representation. Will all the planar representation have same number of faces? Let me tell you the answer, yes. All the planar representation will have same number of faces, and this was proven by Euler. Okay, so Euler proved, it was proven by Euler that if you have a planar graph, then every planar representation, all planar representation will have same number of faces. And Euler also gave a formula to count the number of faces. Okay, so this we will see, don't worry. But I am saying that for any graph, remember, you create planar representation. You can create any planar representation. You can create this or this or this or this, and then you can count the number of faces. The number of faces will always be same. Tell me the answer for this question. We know that every tree is planar graph. How many faces are there in a tree? The answer will be 1. We know that forest is a planar graph. How many faces will be there in the forest? The answer will be 1. Tell me the answer for this question. G is a planar graph with only one face. So, can G contain a cycle? G is a planar graph with only one face, we only have one face, is it possible that G can contain cycle? The answer is no. Think about it. See, if you have a cycle, then what will happen? If there is a cycle, then what will happen? Then at least two faces will be there. Yes or no? If G contains a cycle, then definitely at least two faces will be there. Do you agree with me? Okay. So that is the reason I can say if you have only one face, then you cannot contain a cycle. Tell me the answer for this question. G is a planar graph with only one face. Then what is G? Can anyone tell me? You have a planar graph with only one face. Then what is that graph? That graph is forest. Can I say that graph is tree? Can I say that graph is tree? No, I cannot say, but I can say that graph is forest. Yes or no? Okay, if you have a planar graph with only one face, then I can guarantee it is a forest. But you cannot say that it is a tree. Because for tree you need connected also. Yes or no? So if I ask you this question, connected planar graph has one face. Connected planar graph. Then what is G? Then answer will be this also, this also. You can see a planar graph has one face if and only if it is forest. A planar graph has only one face if and only if that is a forest. Now let's see the next concept, that is degree of a face. See, if you look at any edge, consider this edge A, B. This edge has how many sides? Can you tell me? You think of this edge as a wall. Okay, just consider this edge as a thick wall. Now you tell me, this is your edge. Now you tell me, how many sides are there? This edge has how many sides? So there are two sides, this side and this side. So this is what I'm saying, that basically what you do, think of edge as a wall. Okay, what to do? Think of every edge as a wall. Okay, so you can easily see that every edge has two sides. Every edge has two sides. Okay, now let's see the concept. Degree of a face and the definition. Understand the definition. Degree of a face is the number of sides a face is touching. Okay, please understand. Degree of a face is number of sides face is touching. Okay, so you can see degree of a face is the number of sides, number of sides of edges it will touch. Okay, is this clear? Very simple point. For example, consider this graph. First of all, is this planar representation? Yes, this is planar representation. This is drawing without edge crossing. Now here you can see that these are the graph. These are the faces. This, let's call it face number 1, face number 2. Let's call it face number 3. Let me call this face number 4. And this outer area, let me call it face number 5. Okay. Now you tell me what is the degree of F2? Can anyone tell me the degree of F2? See, this F2 is touching how many sides of the edges? How many sides of the edges? You can see this side of the edge, this side of the edge. How many sides of the edges? You can see 4 sides of the edges. So the degree of F2 will be 4. Okay. What about degree of F1? Degree of F1. How many sides of the edges it is touching? You can see this F1 is touching this side, this side, this side, and also this side. What about F3? This F3 is touching this side, and this side. What about F4? F4 is touching this side of the edge, this side of the edge, this side of the edge. What about F5? What about F5? F5 is touching this side of the edge, this side of the edge, this side, and also this side. So you can easily see what is the degree. For example, if I ask you the degree of F1, that will be 4. What is degree of F2? That will be 4. What is degree of F3? That will be 3. What will be degree of F4? That also will be 3. And tell me what is the degree of F5? That will be 4. Okay, understood? Please tell me. So like this you can find the degree of any face. I hope you understood. Consider this, another diagram I'm giving you. Consider this tree. Okay, consider this graph. Now you tell me, is this planar representation? Yes, this is a drawing without edge crossing. Now you tell me that how many faces are there? There is only one face. Yes or no? There is only one face, F. Now you tell me, what the degree of this face? Remember, degree of a face is how many sides of the edges it is touching. So this face is touching this side of the edge, also this side of the edge, 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 this side of the edge. So you can see it is touching six sides of the edges. So degree of f will be 6. Okay. Is this clear? So the definition is actually very simple. Degree of a face is the number of sides of the edges it is touching. I hope you understood. Okay. Tell me the answer for this question. Consider the given graph. Is this planar graph? Is this planar graph? The answer is yes, because I can draw this graph without edge crossing. Let me do this. Okay, see, I will draw this graph without edge crossing, BC. Okay, then you can see there is D. Okay, so let me draw this graph. For example, I can draw this graph without edge crossing like this. Okay, see, C, D, E, F. And then what I can do? This D, this is adjacent to A, and this is adjacent to this. Then you can see this B is adjacent to here and here. That's it. Yes or no? Is this clear? So I got the planar representation of this graph. We have created, you can see the planar representation we have created. Now you tell me. So is this planar graph? The answer is yes, because I can draw this graph without edge crossing. Now you tell me how many faces are there? Let me know. Okay, so this is the planar representation. Now you can easily find the number of faces, and the number of faces will be, you can easily see that this is like face number 1, face number 2, and face number 3. So there are total 3 faces. Can you tell me the degree of these faces? For example, what is the degree of F1? See, this F1 is touching 4 sides of the edges. Okay, yes or no? What is the degree of F2? This F2 is touching, you can see this side of the edge, 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 this one, this one, this one. Yes or no? So total how many? 1, 2, 1, 2, 3, 4, 5, 6. So that will be 6. And tell me, what about the degree of F3? So F3 is touching this side of the edge, this side of the edge, this side, and this side. So you can see that will be 4. Okay. So very simple. Like this, you can find the degree of faces. Okay. Tell me quickly the answer for these. So first of all, are these planar representation? Yes, these are planar representation. Let me call this graph G1. Let me call this graph G2. Now here in this graph G1, you have these faces, face number 1, face number 2, face number 3. These are the faces. In this G2, there is face number 1, face number 2. And you can easily find the degree also. For example, if I ask you what is the degree of face number 1, what that will be? Degree of face number 1, that will be 4. What is the degree of face number 2? That also will be 4. What is the degree of face number 3? That will be 1, 2, 3, 4, 5, 6. Yes or no? So like this. And here also the same thing. If I ask you what is the degree of face number 1, degree of face number 1, notice this face is touching this side, this side, this side, this side, this side, this side, and this side. Okay, so total how many? So you can see that is 7, right? Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, so you can see degree of 1, that is 7. And what is degree of 2? Degree of phase 2. You can see phase 2 is touching this side, this side, this edge, this side of this edge, this edge, this side. Okay, so you can see that will be 5. Okay, so the degree of 2, that will be 5. Understood? Let's move on. Now let's see handshaking theorem for faces, means degree summation of faces. We have already seen what is degree of a face. Now we will see if we do the summation of degree of all the faces, then what we will get. And this is a very simple result, let me tell you. So let's see the note that if you do the summation of degree of all the faces, okay, where f is a face, where f is a face, if you do the summation of degree of all the faces, then you will get twice the number of edges. Okay, and very easily you can prove it. Tell me why it will happen that the summation of degree of all the faces, that is equal to twice the number of edges. And the proof is very simple, because you already know, because of every edge, this edge, look at this edge, what it will do, it will increase the degree of total degree of faces, it will increase by 2, because actually it will contribute. See, this has two sides. Please focus. This edge has two sides. Okay, so from this side also 1 degree will increase. From this side also one degree will increase. Yes or no? Because of every edge, total degree of faces, the degree summation of faces, that will increase by 2. This is the simple proof. I hope you understood. So very simple. You can see degree of a face, that we have already seen. Degree of a face is the number of sides of the edges it is touching. Number of sides of edges it is touching. Next, you can see every edge has two sides, that you already know. Okay, this side and this side. So that is the reason I can say that. So in the total degree of faces, every edge will contribute a value of 2. That is the reason the degree summation of all the faces, that will be twice the number of edges. For example, you can verify in this diagram. Tell me in this diagram, what the degree of this face, that is 4, degree of this face 4, 3, 3, and degree of this outer face, that is 4. So what the total degree of faces? That will be, you can see, that will be 18. And what the twice the number of edges? What that will be? 2 multiplied. But what is the number of edges here? So you can see that is 4, and there are so total 9 edges. So you can easily see that is also 18. So you can verify very easily. I hope you understood. Okay. So this is the summation of degree of all the faces. In any planar graph, the sum of degree of all the faces is equal to twice the number of edges. Okay. One more important result, that is, for any planar graph, in any planar representation, how many faces of odd degree will be there? Tell me. We know that the summation of degree of all the faces, that is twice the number of edges. So twice the number of edges, that means that is an even value. Okay, just similar to your degree of a vertex. If you remember, the summation of degree of all the vertices, that is twice the number of edges. Okay, so finally what we have number of odd degree vertices is always even. Similarly here, number of odd degree faces, that is always even. Is this clear? So remember, number of faces of odd degree, that will always be even. I hope you understood. Okay. Okay, one more thing, remember, if you see the summation of degree of all the vertices, what that is? That is twice the number of edges. This we already know. If you do the summation of degree of all the vertices. Similarly, if you do the summation of degree of all the faces, that is also twice the number of edges. So basically these three things are same. The degree summation of vertices is equal to the degree summation of faces. Okay. Let's see this question. Here the question is asking how many faces are there and what are their degree. So tell me how many faces are there. Let me know. In this diagram, you can see this is one face. Let me call it face number 1. This is face number 2, face number 3, and there is outer face, face number 4. What are the degree of these faces? For example, the degree of this face number 4. See, this face number 4 is touching this side of the edge, this side of the edge, this side of the edge, this one, and also this one. So tell me. So the degree of F4, that is 6. That is, sorry, degree of F4, that is 7. Okay, degree of F4 will be 7. What is the degree of F3? That is 3. What is the degree of F2? That is 3. What is the degree of F1? You can see F1, what it is touching. You can see this side of the edge, this side of the edge, this side of the edge, this one, this one, this one, this one. Okay, so how much you can see? 2, 5, and 7. Again, you got a 7. Okay, is this clear? Okay, so this side of the edge and this side of the edge. So the answer will be 9. This will be 9. So the degree of F1 will be 9. Degree of F4 will be 7. Okay, you can easily check. Now you can easily verify. Tell me what is the total degree of all the faces? Let me know. What is the total degree of all the faces? You can see 7 plus 9 plus 3 plus 3. So what is that value? That value is 22. And what are the number of edges here? What are the number of edges in this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that is 11. So you can easily see there are 11 edges. So you can easily verify this theorem. And tell me, how many faces of odd degree are there in this number of odd degree faces? That is 4, that is even. Yes or no? Number of odd degree faces will always be even. This we have already seen. Can I give you this question as a homework? So there are 3 questions here. So please take this question as a homework. Pause this video right now and write your answer in the comment. Then you continue watching. Similarly, you can just go through this. This planar representation is given to you, and these are the degree of all the faces. You can check it out. Okay. Let me give you this another question as a homework. This is actually more interesting question. Why this is interesting question? Tell me. Because here you can see this is not a planar representation. Yes or no? On your screen, this diagram is given to you. This is not a planar representation because there is edge crossing here. So first, what you need to do, you need to convert this into planar representation. Then you count the number of faces. Then you find the degree of the faces and so on. Now you tell me one more thing. To count the number of faces, which planar representation you will consider? See, this diagram, this graph has many planar representation. So to count the number of faces, which planar representation you will consider? You can consider any planar representation. Okay, is this clear? But let me tell you one thing. See, you can consider any planar representation to count the number of faces. The number of faces will not change, but the degree that can change. Okay, let me give you one example here. See, consider this diagram. This graph, look at this graph and tell me, this graph, are they same graph? Are they same graph? Let me know. On your screen, two graph I am giving you. Yes, they are same graph. And these are planar representation or not? Both are planar representation. Yes, there is no edge crossing here. There is no edge crossing here. So both are planar representation. You can notice one thing. The number of faces will not change. For example, this is face number 1. This is face number 2. Okay. Number of faces here also 2. Here also number of faces is 2. Okay. Is this clear? Please tell me. But you can see their degree will change. For example, here, what is the degree? Degree of F2. What that? Here you can see degree of F2 is 4. And what is the degree of F1? Degree of F1, 1, 2, 1, 2, 3, 4, 5, 6. That will be 6. Okay, in this diagram, you tell me what the degree of F1? That is 4. And what the degree of this F2? That is 6. Yes or no? Is this clear? So here, remember, here unbounded region has degree 4. Okay, I hope you understood. Here unbounded region, degree of unbounded region. I can say that here degree of unbounded region, you can see that here degree of unbounded region, that is basically 4. And here degree of unbounded region is 6. Okay. So very simple point. Again, I'm telling you that which planar representation you consider, it will not matter if you are finding the number of faces or if you are finding the total degree of the faces, because total degree of all the faces, that will be twice the number of faces. Yes or no? Okay. So this is what I'm saying. If a graph is given to you, then first you convert this graph into a planar representation. Any planar representation you can consider. Okay. And then you find the number of faces, and then you find the degree of the faces, and so on. Now let's see some important questions related to degree of faces. Tell me this question. Can degree of a face be 3? Is it possible that degree of a face be 3? Yes, this is possible if you have a triangle. See, degree of a face is 3. If you want degree of a face to be 3, then definitely it should be surrounded by 3 edges. Yes or no? Degree of a face will be 3 if it is surrounded by 3 edges. So you can see in this situation, I can say here the degree of this face is also 3 and the degree of this face is also 3. Yes or no? Here you can see the degree of F1 is also 3 and degree of F2 is also 3. Tell me the answer for this question. Can degree of a face be 0? Can degree of a face be 0? Yes, it can happen if there is no edge. Basically, if you have edgeless graph. Yes or no? This can happen only in edgeless graph. Only if graph is edgeless graph. Yes or no? There is no edge. if graph is ageless graph. Do you agree? If there is no age, then degree of phase will be 0. Null graph, empty graph, ageless graph. Only in this situation, the degree will be 0. So you can easily see these are the 2 points we have seen. For any planar graph, degree 0 phase exists. When degree 0 phase exists, if and only if graph is ageless. Okay, remember, in your graph, if you have a graph, then degree 0 phase will exist. If and only if the graph is ageless. If there is no age, then degree 0 phase will exist. If you have at least one age, if G has at least one age, if your graph has at least one age, connected or disconnected does not matter. Your graph can be connected or disconnected, but if it has at least one age, then no phase can have degree 0. Yes or no? Very simple. Tell me the answer for this question. Can degree of a phase be 1? Is it possible that degree of a phase be 1? You can try. Degree of phase can never be 1. See, for example, if you have one age, let's assume, if you have this age, then also degree of this phase is 2. Are you getting my point? Here also degree of phase is actually 2. See, whatever you do, for example, if you have no age, then degree will be 0. Here degree is 0. Here degree is 2. So this is what I'm saying, that whatever you do, degree of phase can never be 1. Please understand. Degree of phase can never be 1. You can easily check. Now let's move on. We study only simple graph, remember? All the time we only study simple graph, I told you. Means our graph are simple undirected graph. They can be connected or disconnected. Okay, our graph can be connected or it can be disconnected, but our graph are always simple undirected graph. Okay, now find all possible simple connected graph which contain some phase of degree 2. Just take your copy pen and you try this. See, very simple question. Find connected graph. You must find connected graph which contains some phase of degree 2. Is it possible? In a connected graph, can you have phase of degree 2? Only one such graph is there. Let me tell you. Okay, there is only one such graph, only K2. Other than this, there is no connected graph which has degree of phase 2. Means this is the only graph K2. If you take, for example, this K2 graph, okay, means this single age, you can see this graph. If you take, then degree you are getting is equal to 2. Other than that, remember, if you take any other graph, you can never get degree of phase equal to 2. Okay, is this clear? Please tell me. So very simple point. So ultimately this is the conclusion. These conclusions are important. Read this. Basically, degree 1, degree 2, degree 0 phases, these are very limited. Please understand. If your graph is connected, think about it. If your graph is connected, I'm talking about connected graph. Now degree 1 phase can never exist. Yes or no? You already know. Degree 1 phase can never exist. You can never have degree 1 phase. Whatever graph you take, connected, disconnected, whatever graph you take, degree 1 phase can never exist. Okay. Now, if you are taking connected graph, then degree 2 phase will exist if and only if your graph is K2. Means other than graph K2, if you take any graph, then degree 2 phase you can never find. Degree 2 phase will never exist. Okay. And similarly, degree 0 phase will exist. If you are talking about connected graph, then degree 0 phase will exist if and only if G has one vertex. Let me tell you the conclusion. The conclusion is that if you have at least 3 vertices, think about it and tell me. Let's assume you have a connected graph with at least 3 vertices. Now what will happen? If you have a connected graph with at least 3 vertices, then remember, degree of every face will always be greater than equal to 3. This is what I want to tell you, that degree 1, degree 2 and degree 0, degree 0, 1, 2, these faces are very limited. Okay, very limited. You can only find if you have number of vertices less than equal to 2. Okay, then you can find. But if your graph is connected and number of vertices is at least 3, in your graph, if you have at least 3 vertices, then degree of every face will be at least 3. So this is the note you can easily read here, that in any connected planar graph with at least 3 vertices, degree of every face will be greater than equal to 3. Is this point clear? Degree of every face will be greater than equal to 3. Now let's solve some important questions related to planar graphs. One by one, you tell me the answer. First, let me tell you some notations. If G is a planar graph, it can be connected or disconnected. Remember, it can be disconnected or it can be connected. What is C? C is the number of connected components. F is the number of faces. V is the number of vertices. E is the number of edges. Now, tell me the answer for this question. Let G be a planar graph which can be connected or which can be disconnected. From G, if we delete one edge which is part of some cycle, then how these V, E, F, C will be affected? V means number of vertices, E means number of edges, F means number of faces, and C means number of connected components. I am talking about planar graph. It can be connected, it can be disconnected. Now, from this graph, if you delete one edge which is part of some cycle, then how these values will be affected? Also, from this graph, if you delete one edge which is not part of any cycle, then how these values will be affected? This is what I want to ask you. Let me ask you one by one. But first, let's see what is a cyclic edge. Let's see the definition of cyclic edge. Cyclic, the name itself is telling you cyclic edge means edge which is part of some simple cycle. Okay, so remember, if there is a edge, for example, consider this edge. If this is part of some simple cycle, then this will be called cyclic edge. Is this point clear? Cyclic edge means edge which is part of some simple cycle. If this edge is part of some simple cycle, then this will be called cyclic edge. What is acyclic edge? Edge which is not part of any simple cycle. Okay, that is called acyclic edge. For example, consider this diagram. In this diagram, what are the cyclic edges? What are the non-cyclic edges? Can you tell me? So let me write it here. Let me draw that blue. Okay, let me draw that blue means acyclic edge. Okay, and red, I will draw the red means cyclic edge. Red means cyclic edge. Okay, is this clear? What I'm doing? So remember, I will draw with red the cyclic edge. Cyclic edge means which is part of some cycle. See, this is a simple cycle or not? On your screen, you just think about it. Is this a simple cycle or not? Yes, this is a simple cycle. You start here. This is a simple cycle. So all these edges, these are cyclic edges. Cyclic, 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 cyclic. These edges are cyclic edges. For example, this is a simple cycle. So these are also cyclic edges. For example, this is also simple cycle. So these edges are also cyclic edges. Okay. So what are the non-cyclic edges? Or I can say acyclic edges which are not part of any simple cycle. You can see this is acyclic edge. You can see this is acyclic edge. Okay, is this clear? What are cyclic edges? What are non-cyclic edges? You can see cyclic means edge which is part of some simple cycle. Okay, this edge which is part of some simple cycle, this is cyclic edge, some cycle. Okay, similarly, acyclic edge means which is not part of any simple cycle, that is acyclic edge. Okay, now very interesting question I'm asking. You tell me the answer. If I delete acyclic edge from this graph, then how number of components, number of faces will be affected? You let me know. See, at this moment, what are the values? Can you tell me what are the number of vertices here? You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, number of vertices is 12. What are the number of edges right now? You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Number of edges is 14. What are the number of connected components? Only one. What are the number of faces? How many faces are there? There are 4 faces. Okay, this is the initial situation. Is this clear? This is the initial situation. Now you tell me, if I delete acyclic edge, I am deleting acyclic edge. So you tell me, if I delete some, for example, let me delete this acyclic edge. This is acyclic edge, yes or no? Okay, see, this is look at this edge. This is acyclic because this is not a part of any simple cycle. So this is acyclic edge. Okay, if I delete this, let's zoom. Then tell me how these values are affected. New. Okay, these were old. These were old. Now the new values will be what? You can see Number of connected components increasing by 1. Did you notice? It is increasing by 1. Okay, I can say that number of connected components will increase by 1 plus 1. There is increment of 1. And what about number of faces? What about number of faces? You tell me. Tell me number of faces. If I delete this edge, what will happen to the number of faces? That will be unchanged. You can check. See, if I delete this edge, still I have 4 faces. You can check. There will be outer face. There will be outer face like this. Okay, so you can see number of faces is unchanged. And number of edges, that is I am deleting one edge, so it will be 13, and number of vertices will be unchanged. So basically just focus on number of components and number of faces. Okay, so finally you can easily see if I delete acyclic edge, then number of components will increase by 1 and number of faces will be unchanged. Okay, you can say this, you can see the same thing. See, this is also acyclic edge. Yes or no? Okay, let me delete this. Let me delete this edge. Now tell me what will happen. If I delete this edge, then what will be the new number of components? New values. These were the old values. You tell me the new values. New values will be, if I delete this, the number of components is increasing by 1. Yes or no? Now number of components will be 2. Okay, because this vertex. See, this vertex will be one component and the remaining graph will be one component. So number of components will be 2. And number of faces will be unchanged. Okay, is this point clear? Number of faces will be unchanged. I hope you understood. Of course, number of edges reducing by 1 and number of vertices is same. So what is the conclusion then? Can anyone tell me? You tell me the conclusion. The conclusion is very simple, that from a planar graph which can be connected or disconnected, if we delete edge which is not part of any cycle, if we delete edge which is not part of any cycle, we are deleting edge which is not part of any cycle, means we are deleting acyclic edge. Okay, so if you delete acyclic edge, then tell me what will happen. Then you can see number of components will increase by 1. Number of components increase by 1. Please tell me, understood this? Let me know. Number of components will increase by 1 and number of faces will be unchanged. Okay, I hope you understood this. This is very simple point. So this is very important actually. In the GATE exam, they can ask you these true false statement. For example, if we delete acyclic case, then what will happen? If we delete cyclic case, then what will happen? How the number of components will change, how the number of faces will change. So you can see from any planar graph, in any planar representation, if we delete one edge which is not part of any simple cycle, means if we delete acyclic case, then remember number of components will increase by 1 only. Number of components will increase by 1 and number of faces will be unchanged. This is what will happen. Now similarly, you tell me what about the cyclic edges. So again, you can see the old values. First you focus, old values are number of vertices 12, number of edges 14. Yes or no? These are the old values, 12, 14. Number of components 1 and number of faces, that is 4. So these are the old values. Now you tell me, if I delete cyclic edge, then what will happen? What will happen to the number of components and number of faces? Mainly you tell me about these. So for example, let's assume I am deleting a cyclic edge, remember. Okay, let me delete this cyclic edge, then let me, what will happen? See, this is part of some simple cycle. Yes or no? This cyclic edge, this is part of some simple cycle. If I delete this edge, then two faces are merging. Do you agree with me? If I delete this edge, remember this is a cyclic edge. This is a cyclic edge because this is part of some simple cycle. So this is cyclic edge. If I delete this, then which two faces are merging? Can anyone tell me? By deleting this, you can easily see that F2 and F4 merging. F2, F4, these are merge. Merge, yes or no? These are merging. So tell me, number of faces will be what? That will decrease by 1. Number of components will be unchanged. You can easily notice because you are deleting the cyclic edge, which is part of some simple cycle. If you delete this edge, number of components is unchanged, but number of faces is decreasing by one. Number of faces that is decreasing by one. Number of components unchanged. Okay. Similarly, you tell me, for example, if I delete this cyclic edge, this is also cyclic edge. Let me delete this. You know that this is also cyclic edge. This is also part of some simple cycle. So if I delete this, now you tell me which two faces are merging because of this deletion. Because of this deletion, you can see that F4, F3 merge. Okay, so you tell me number of faces will decrease by one. Do you agree? And number of components will be as it is same. So what is the conclusion you want to give me? Tell me. You can see from any planar graph, any planar representation, if I delete an edge which is part of some simple cycle, means I am deleting cyclic edge. Means I am deleting cyclic edge, then tell me what will happen. You can easily see that faces will decrease by one. Okay, because two faces will merge. This is what we have seen. Two faces will merge. So faces will decrease by one. And what about components? If you are deleting a cyclic edge, which is part of some simple cycle, then number of components will be unchanged. Understood this? Very simple point. Okay. In this diagram also you can see, tell me what are the cyclic edges, what are the acyclic edges, let me know. Here, let me write cyclic edges. Let me draw by red, cyclic edges, and acyclic edges, let me draw by blue. So tell me, what are the cyclic edges? Cyclic edges means which are part of some simple cycle. For example, this is a simple cycle you can see. So this is cyclic edge, cyclic edge, cyclic edge. Okay, you can see this is simple cycle. So this is cyclic edge, cyclic edge, cyclic edge. You can see this is a simple cycle. This is cyclic, cyclic, cyclic. Okay, yes or no? So these are the cyclic edges. What are the non-cyclic edges? Acyclic edges, which are not part of any simple cycle. This is not part of any simple cycle. This one, yes or no? These are acyclic edges. Now, can you notice one thing? That okay, right now, what is the old data? Let me know. You just tell me the data, old data, the original data. You tell me how many faces are there. Number of faces. Here you can see number of faces. For example, let's call it F1, let's call it F2, and there is F3, F4. Okay, so you can see that number of faces is 4. And what are the number of components? That is 1. Okay, now you tell me what will happen if I delete cyclic edge. If I delete, for example, if I delete, let's assume this is cyclic edge. Okay, take any cyclic edge. Okay, for example, let's take this E1. So if I delete E1, then what will happen? Let me know. Quickly tell me. If I delete this edge is gone now. Now number of components will increase. Do you agree? But number of faces will be as it is. Similarly, if I delete some cyclic edge, for example, let me delete this E2. Okay, take this E2. So if I delete this E2, then what will happen? If I delete this E2, then F3 and F4 will merge. So here you can see that number of faces will be reducing and number of components will be same. Okay, so that's it. I hope you understood this point. Now let's move on. So tell me the answer for this question. If you have a planar graph, connected or disconnected, in any planar representation, remember, if we delete edge, which is part of some cycle, then how these are affected? Did you understand? If we delete edge, which is part of some cycle, means if you delete cyclic edge, then remember, number of faces will decrease by one, number of components will be unchanged. This is what we have already seen. And if you delete edge, which is not part of any cycle, then what will happen? The number of components will increase by one and number of faces will be unchanged. These simple things we have already seen. Tell me the answer for this question. Which of the following is never possible? Never. G is a planar graph. It can be connected or it can be disconnected. From G, we are deleting one edge. I am deleting one edge. Then Remember this edge that I'm deleting, either this can be cyclic or this can be acyclic. There are only two options. Yes or no? Do you agree? See, this edge, either it can be cyclic or it can be acyclic. There is no other choice. Yes or no? So if you delete cyclic edge, then what will happen? If you delete this edge, then what will happen? Cyclic edge, if I delete, then f will reduce by 1. Okay, for number of faces, I can say it will be -1. Number of components will be unchanged. Okay, unchanged. And if I delete acyclic edge, then what will happen? The number of components will increase by 1 and these will be unchanged. One of these will definitely happen. Yes or no? So very simple point, which is never possible. F decreases, this is possible. F decreases, this is possible. When this is possible, F is decreasing, this is possible if you delete cyclic edge. Is this clear? Please tell me. If you delete cyclic edge, then F decrease possible. C increase possible. When C increase possible, if you delete acyclic edge. Okay. Both happen simultaneously. That can never happen. See, you are deleting one edge. Either it can be cyclic edge or it can be acyclic edge. So either this will happen or this will happen, but both cannot happen simultaneously. Neither happens. No. If you are deleting one edge, then one of them will definitely happen. Yes or no? Either this will happen or this will happen. One of them will definitely happen. Understood? And tell me, what about F increase? Can it happen? F increase. You are deleting one edge. Is it possible that number of faces can increase by deleting one edge? Number of faces can never increase. What about C decrease? Number of components can decrease. Is it possible number of components can decrease if you are deleting one edge? No, number of components cannot decrease. I hope you understood. Okay. So what is possible, what is not possible? So clearly, did you understand? Please tell me. Now let's see Euler formula for planar graph. This is very important formula from the GATE exam point of view. Let me tell you, I told you that any planar graph has many planar representation. For example, your K4 complete graph on 4 vertices, we can create many planar representation of K4. Now you might be thinking that all these planar representation, will they have same number of faces? Let me tell you, the answer is yes. And this was proven by Euler. So Euler proved that for any planar graph, all the planar representations will have same number of faces. Okay, will have same number of faces. And Euler also gave a formula to calculate, to count the number of faces for a planar graph. So remember, if a graph is given to you, planar graph is given to you, and they ask you how many faces are there, then either you can apply the Euler formula, or what you can do, you can convert this into a planar representation. Any planar representation is fine, because Euler proved that number of faces in all the planar representation will be same. So you can convert this graph into any planar representation, and then you can find the number of faces. Or what you can do, you can simply apply the Euler formula and you can find the number of faces. So Euler proved one very interesting result, and that is, for any planar graph, connected or disconnected, in every planar representation the number of faces will be same. Okay, for any graph, for any planar graph, whatever planar representation you take, there can be 10, 20,000 planar representation can be there, but the point is every planar representation will have same number of faces. And the formula also he gave. Okay, so let's see the formula for Euler formula, and that is very important from the GATE exam point of view. So if G is a planar graph, it can be connected or it can be disconnected. Then let's assume C means number of connected components, F means number of faces, V means number of vertices, E means number of edges. Okay, these are the notations. Now let's see the Euler formula. Euler formula is very simple. It is saying that V plus F equal to E plus C plus 1. Means in any planar graph, remember, Euler formula is only applicable for planar graph. If your graph is not a planar, then it is not applicable. Yes or no? So this is for planar graph. Your graph can be connected or disconnected, that is fine, but your graph must be planar. Means there should be some way to convert your graph, to draw your graph without edge crossing on the 2D plane. So if your graph is planar, then Euler formula says that V plus F equal to E plus C plus 1. Okay, number of vertices plus number of faces will be equal to number of edges plus number of connected component plus 1. Okay, and remember this this formula, I can say this will be true for every planar representation of any planar graph. Okay, so this does not depend on a particular planar representation. So using this formula you can easily calculate, you can easily count the number of faces in the planar graph for any planar representation. Okay, is this clear? No. So let's see what this Euler formula. Let me write it because this is very important. So let's assume G is a planar graph. Okay. Then formula says that this Euler formula, this says that V plus F is equal to E plus C plus 1. Okay. Is this clear? This is the formula. Don't forget about this formula. Very important formula. V plus F equal to E plus C plus 1. Tell me one thing. If graph is connected planar graph, then what will happen? Tell me how this will change. If your graph is connected planar graph, now what will happen? Very simple. If your graph is connected planar graph, then remember number of components will become 1. There will be only one component. Yes or no? So now your formula will become V plus F equal to E plus 2. Okay, so this is the formula for connected planar graph, and this is the formula for all the planar graph. Okay, very simple. I hope you understood. So you can just remember this V plus F equal to E plus C plus 1. Okay, is this clear? And if your graph is connected, then you can say V plus F equal to E plus 2, because in this connected situation, the number of components will become 1. You can see in this graph, you can easily find the number of faces. Okay, so you can just apply the Euler formula. You already see that V plus F is equal to E plus C plus 1. Because this is connected graph, so C will be equal to 1. Okay, number of edges you can see 15, number of faces you can calculate. See, this is a planar representation. So you can calculate the number of faces very easily. Okay, this is a face, this is a face, and so on. So you can easily see that using the Euler formula also you can calculate number of faces. Tell me the answer for this question. This graph is planar. Okay, on your screen, I have given you one graph which is planar. You don't have to check is it planar or not. I am telling you this is planar. But tell me, this drawing, is this planar representation? This drawing, is it a planar representation? No, this is not a planar representation, because in this drawing, edges are crossing. Now you tell me, find the number of faces if I ask you. Then tell me, will you convert this into a planar representation and then you calculate number of faces? Will you do that? Will you do that? That first you convert this into planar representation and then you calculate number of faces. Will you do that? You can do that, but you don't have to. You just apply the Euler formula. Yes or no? See, if any graph is given to you, and if any planar graph is given to you, it is already given that it is a planar graph, then remember to find the number of faces. You don't have to convert the graph into planar representation, because you can apply the Euler formula. The Euler formula will give you the answer. Or what you can do, if you don't want to apply the Euler formula, then you convert your graph into a planar representation, and then you can count the number of faces. Okay, so here actually very easily what you can do, you can just apply the Euler formula. You already know that Euler formula means V plus F is equal to E plus C plus 1. Tell me, in this graph, what is the number of components? You can see 1, 2, 3. Number of components 3. What are the number of vertices? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What are the number of edges? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so number of edges are 10. That's it. So from here you can see F will be equal to E plus C plus 1 minus E V, and that will be equal to 4. Okay, you can easily calculate. Please tell me, did you understand? Let me know. So like this you can do. Here also you can see that Euler formula will work. Okay, here also you can easily see There is only one component, so v plus f equal to e plus 2. Okay, you can check the Euler formula will work here also. Okay, so that's it. We have seen the Euler formula. I hope you understood. So let's solve some gate exam questions based on Euler formula. I told you that Euler formula is very important for the planar graph. So let's see some gate previous year questions. Tell me the answer for this question. This is gate 2005 question. Let G be a simple connected planar graph with 13 vertices and 19 edges. The number of faces in the planar embedding, planar representation of this graph. See, already connected is given to you. What it means? It means C is equal to 1. Okay, so you can apply the Euler formula. So Euler formula says that V plus F is equal to E plus C plus 1. Now this C value is already 1 because the question is saying it is a connected graph. So finally you can see 13 vertices are given to you. 13 plus F is equal to 19 plus 2. And F value, what that will be? That will be equal to 21 minus 13 and that will be 8. Yes or no? So for this question, answer will be option B. Simple question. Let's solve this GATE 2021 question. Undirected connected planar graph. Connected means number of components is equal to 1 and it is a planar graph. There are 8 vertices, 5 faces. Then number of edges. You can apply the Euler formula. Euler formula says that V plus F is equal to E plus C plus 1. Because it is a connected graph, so C value will be 1. So from here the E value will be V, that is 8, plus F, that is 5, minus C minus 1. Okay, so you can easily calculate. The number of edges will be 11. Okay, so these are simple questions based on planar graph. I hope you understood. So that's it. This is your graph theory summary part 4. In this lecture we have seen bipartite graph, we have seen trees, and we have seen planar graph. All these are very important. Yes or no? We have done a lot of questions based on tree, based on planar graph. Okay, so everything we have seen related to planar graph, bipartite graph, and trees. So please tell me, did you understand each and everything? Let me know. Okay, thank you everyone. Please share your feedback in the comments. Thank you.